Welcome back, everyone, to the second day for the data science meeting in astronomy. So yesterday we had a lot of introductory talks about machine learning, different things that are going on, so that you get up to speed. But then today we are going to have about 7 talks in total, which will focus on the use cases and how machine learning is being used in astronomy currently. So you'll hear from areas which are quite diverse, and also methods, I think, which are also quite diverse. But you would have at least had some background or had some, would have heard about some of the methods that are being used yesterday. So first, we'll start with them from NCRA. So he's going to talk about real-time AI applications for classifying fast radio transits with GMR. Please.
Thank you. Good morning, everybody.
It's here.
Okay, yeah,
I think it should be okay. It should catch.
Yeah. So good morning, everybody. And I was looking at the your schedule on yesterday, and I think you have went through a kind of various topic on machine learning, deep learning, AI. So what I'm going to try to do here, actually, just take up one of the kind of use cases which is right now happening at GMR2. I'll give you maybe one slide about GMRT also, because definitely you have gone through yesterday. Some of you maybe first time. So I'll talk about very briefly about that telescope where we are doing these use cases, and then mostly discuss about the use case and how we're going to deal with that like in real time, because real time is important here. It's not only the AI, but it has to do a certain amount of job in a given time frame when the data is still coming from the telescope. Okay, so this is a large project. I'm just presenting on behalf of the big team. So we have various teams. We have the AI team. So I'll just put it in red, because that is what we are going to talk about. What are the work is being done by the AI team? It's like which consists of a team from a member from NVIDIA, NCRA, and also IIT Palakkad. It is working under the NVIDIA AI Technology Center collaboration. So I'll just talk about the result from there. But there's a data center team, CDAC and NCR are actually continuously working on that. There is Oxford and NCR is working on the HPC team also, some detection. So I'll give you one slide about detection problem, because once you know the detection is there, then only you can do AI for classification. That's all. And these are the 3 students. They are actually, most of the work which I'm presenting is actually done by these students, not done by me. I'm just kind of looking at it. So they are the people who should be getting credit out. Okay. Okay, so first, before I jump into the transient, or especially the first transient, these are the 3 big questions which you are looking for when you say that, okay, we'll do the classification in real time and try to find out the real transient real time with the telescope like GMRT. The questions are like whether there is a missing matter in the universe. So this is something which you already know from the plant, and then we just trying to find out maybe more quantitative way over a large range of redshift, what is the missing matters in the universe. We'll find out the magnetic field evolution in the universe at a cosmological distance, and then also we basically, like everybody, all the astronomical experiments are actually there to look for the civilization, if there is any. So there's kind of the inference from that also can come through the data. So these are very big questions. These are very open questions. I'm not going to kind of go to each of these questions, but just to motivate you, what are the questions lying behind when you're actually targeting the first transient. But now come back to the telescope for one slide, and then go to the exact specific object, and the exact physics which we're going to target from that, and then how we're going to do it. So like the GMRT, Giant Meteor Radio Telescope, is like 100 kilometers from here, and the telescope is an array of telescopes. Each of them is 45 meters, and they are operating over a large frequency range, almost from 100 megahertz to 1500 megahertz. And so it's one of the largest radio telescope array operating at a low frequency. That definitely tells you that it can be more sensitive also. And then it actually has like when I'm talking about sensitivity, it matters from 2 things. One is how big is the telescope, and what is the operating frequency of the telescope in terms of operating bandwidth. So that's why the GMRTs also have a very wide operating bandwidth. It's almost like 400 megahertz, and that it is excellent telescope for doing time domain study, apart from all the other study also. Because in the time domain study, you start with the understanding that whatever the emission is coming from the objects, they are broadband in nature. If they are broadband in nature, then you try to kind of collect the radio photons at wider bandwidth as possible, and that is what GMRT allows you to collect the radio photon over 400 megahertz bandwidth. Then it becomes a very excellent sensitive instrument. That's all for GMRT. We need to know in this talk. Now, what are the objects we are looking for? So anyway, some of these numbers may be outdated in terms of how many objects are still there, because people keep on searching for them and finding every day new and new objects. Now, right now also, say, if I look at this slide, like few minutes from now, maybe this number will be changing. But anyway, so we can just take this number as it is right now, and then let's see that what are the different kind of objects you are going to find when you are talking about time domain universe. And time domain universe actually start from radio pulsar, where you see there is a neutron stars. Basically, it is a rotating, highly magnetized rotating neutron stars, and then the emission is coming from the neutron star magnetosphere. So as it rotates through you, the line of sight cuts through you, the emission cone, and you find it regular pulses, and they are periodic in nature because it's a rotation beam which is actually cutting your line of sight and giving you emission. Now, since it's a regular thing, basically you find a periodicity of the pulse underlying. So basically, it's a periodic object, and so that's why it's called pulsar. It's pulsating radio source, but it's a periodicity. So that's basically when you look for those kind of objects, you look for the periodicity, you look for the individual event as well as the underlying periodicity of this. Now, if you move from the periodicity to a little bit aperiodic signal, then you become a rotating radio transient. It's called RRAT in short form, and this is actually a galactic event. So when I'm talking about pulsar, they're mostly galactic. There is no point to think that pulsar is only limited to our Milky Way. There are pulsars outside the Milky Way also, but you are not sensitive enough to see them. So that's why it is till now the galactic observable universe which you are seeing. Similar rotating radio transient is also neutron stars. It is actually also rotating. It has a periodicity, underlying periodicity, but because of the sporadic nature of this emissions, because of various emission conditions, the emission gets ceased during the observation, and you only see some sporadic pulses. So basically, some sunset you say distance between two pulses is actually more than the one period of the rotation of the neutron star. So that's why you don't see underlying periodicity during the observation, and you call them transient. So you call them rotating radio transients. Now, if you see the pulsar is there are another class of pulsar, and since you have maybe you have heard and you will be hearing about the gravitational wave physics, and then the gravitational wave physics is one of the contributors in the low frequency gravitational wave physics called millisecond pulsar. So they are very stable rotator in the sky, and since they are very stable rotator, you can use them as a clock in the sky. So that's why this is pulsar, but this is actually another subclass of pulsar, interesting because of its own properties. So that's a millisecond pulsar, and it comes out with various kind of properties, various kind of evolution in terms of because they are binary in nature. So there's an interaction and all those things make the things much more complicated. Now, when you move from regular pulses, either in the form of pulsar or millisecond pulsar, to giant pulse kind of phenomena, when the things are actually now when I'm talking about pulsar, each of these pulse still is like hundreds of microsecond wide. Okay, it could be millisecond wide, it could be a few hundred of millisecond wide. But when I'm talking about giant pulses, each of these pulses is like a microsecond or less than microsecond, 100 of nanosecond wide. Now that is what actually talks about where from this emission has come. It could be somewhat different. The emission entity from the giant pulse could be somewhat different than the pulsar. And we try to see that because it could be at different places in magnitude where this giant pulsar emission is coming. But okay, but apart from the physics in terms of the observable, this actually is a very narrow tiny pulse. It's like a couple of nanoseconds is the width of the pulse. So basically now when you're looking for these giant pulses, you have to be capable enough to find some couple of tens of nanosecond pulse, which is emitting. It's a very strong, bright, but they're just lasting over the nanosecond. Now, if you observe that pulse in millisecond order, then your sensitivity to detect the pulse will go down because you'll add a lot of noise in the near data. Now, when you're talking about another object, it's called magnetars. This is also a rotating neutron star, but it's not rotationally driven. It's a magnetically driven. Why this object is important and interesting because it fills that lot of transit which I'm talking about. Many of their progenitor model, underlying progenitor model could be magnetars kind of thing. So now we see a lot of galactic magnetars, and then some of them are radio observable, that is radio bright, and you just see that various sporadic pulses from there. There is a rotation period associated with it, but you see them as a kind of single pulses because you see them as an aperiodic event when you observe them. But when you observe for longer duration of time, you find that underlying periodicity from this structure. But they are magnetically driven, so the energy is coming from the magnetic field, not from the rotational kinetic energy. Now the last object, which is our interest of today, is called first radio burst. So the first radio burst is basically as the name says, the first is basically it has to be first in terms of time scale. So we're talking about millisecond or couple of hundreds of microsecond time scale when the event is lasting, and the radio basically is active in radio and the burst-like nature. So there is no underlying periodicity which is there in the magnetar, pulsar, rotating radio transient, and pulsar. So there is no kind of underlying rotational periodicity which can be associated with the FRD till now, which you see in the other neutron star objects. But otherwise, in the observational frame, they are almost kind of similar. Only thing, they are of extragalactic origin. So that's why when you're looking for those objects, you have to look for large distance. That means your observable parameter space increases vastly. Because now still this up to this point, we are only looking at the galactic regime. So that means you have to correct for the dispersion effect. That's the how when the electrons are traveling through this medium in the ISN, they get dispersed because of the different frequency dependent group velocity. So we have to correct up to some region because we are only looking at the edge of the Milky Way. But when you're looking for the FR, you are going outside the Milky Way. So that means your observable universe increasing. So your parameter space increasing. Your data explosion happens in terms of computation as well as data rate. So there are different varieties of first radio burst. Some of them is kind of one-off. This happens only one flash, a couple of milliseconds, and some of them are repeating events. They are actually find them again and again in multiple times. So people are looking for it, and Sriharsh can definitely have more on the FRB because the giant telescope where he's working on actually find it's actually the telescope which is leading the FRB science and discovery till now. Okay, so yes. Okay, so I'll only move towards the topic of today's, which is like AI for classifying the first radio burst. But before that, I'll just give you a kind of one-page summary of the project which I'm talking on, and then the questions. Now this is a very direct questions. Now, initially I've given you much more broader questions, but now what we are looking for. Okay, so this is actually a real-time kind of petabyte clock instrument, which has a combination of HPC AI and then looking for the event in the sky. And the questions which are asking for, as you see that the small cartoon shows the FRB and there's the R, and then large distance to travel, which goes through all the way. The FRB sitting in the external galaxy, it goes to the ISM of the host galaxy, it goes to the intergalactic medium, and then the ISM of our Milky Way. So it's actually traveling through the large distance. So basically, it has imprint of each of this medium and their annals content, which basically give us kind of standard content to kind of probe all the baryons which are actually there all along the line of sight. So basically, somewhere it's actually finding the missing baryons or missing matters. It also, as you can just is existing for a couple of milliseconds, you can actually use the FRB to kind of know the magnetic field, the evolution of magnetic field, either wherever it is happening in the host galaxy or through the IGN. Then it basically start doing various kind of FRB cosmological questions. And one of the things actually what this project and whatever I'll be talking about will be actually try to address that was a key science case for the square kilometer array. Some of you may not have heard about it. The square kilometer is a kind of ultimate telescope which people are building in terms of radio community. It's a square kilometer. As you said, it's a collecting area is square kilometer. And it's going to be a very sensitive telescope. And there are key science questions, whatever is there. Some of the key science questions we are trying to address by the spotlight project. But is a subset of sensitivity case. So anyway, so if you, as this saying that is going to operate in the all frequency domain, so that means you have to be ready with your classifier to kind of see a different environment which is coming in all this large frequency range. And if you do everything correctly, then you could see a large number of cross radio bursts in the next 3 years of science operation. Now, I will say that I will go through one slide of very brief detection problem. Otherwise, because just to give you some illustration of the parameter space what we're working on. So we say two parameter space. One is the dispersion, that means what distance you're looking for the object. Another is how wide this object is, that means what is the width of the object. So this cartoon shows you the effect of dispersion. So basically, this is the pulse because this is the actual true pulse, and these are the two different pulse. One of them is undercorrected in terms of dispersion, and another overcorrected. So this is the frequency, and this is the time. In each plot, the y-axis is the frequency, x-axis is the time. You can see this aligned in frequency, and these two are not aligned in frequency. So basically, it is telling that if you correct the dispersion measure correctly, that means if you kind of predict the distance to the object, or not in the distance to the object, but the ionized material up to the distance to the object properly, then you can actually get the proper pulse shape out. But if you're not doing that correctly, then you actually see the pulses broaden, and in some sense, you can easily say the signal to of that pulse will decrease. So that means your detectivity capability will decrease if you actually not corrected the ionized medium effect properly. So that means that, and since you don't know the distance, you have to go through the large number of such correction, because in some FRB coming from one distance, another FRB coming from another distance. So basically, the number of operation is kind of depend upon how many dispersion measure trial you are doing. And now once you correct this thing, the next thing is that you don't know the shape of the pulse. Right? Pulse shape is unknown to you. So next thing what you have to do, basically in mathematical term, you have to do a convolution to actually find out the actual pulse shape. So these are the two basic mathematical operations which we'll do in the deterministic fashion in the detection part. This is not AI. AI is something which is not explicitly programmed for. When something explicitly programmed for, then it's not a statistical problem. So these are actually a statistical problem where you program your instrument to find out the proper dispersion measure and proper root of the pulse. Now, having known that, now there the problem starts, because you say that I have made a detection of this thing, but like say this card will show you that. So this is actually three of this geometric view, three of the direction of the sky. You are seeing the signals, and you can start seeing that detection problem actually brings out all these things. Okay, now where is the FRB sitting? Right? So where is the real celestial pulse sitting? So you can see some of this is celestial pulse, but now there are many things coming there. So now the challenge is to AI to figure out that out of also these are real pulse. So out of all these things, which is the real? The detection is saying, okay, there is a pulse and this is a dispersion measure and this is a width. Your match filter, your convolution match properly. Okay, so now the problem comes to this part. Okay, so you have your module, HPC module is properly perfectly work and give you detection, but now the problem lies into this into the domain of ML/DL. So ML is machine learning and DL is deep learning. So I'll go to the one slide of try to distinguish between these two. And then the data rate which will be challenging is like 2 petabyte per day. So that is a real-time data rate which you have to process, and you have to make a correct decision at this point as far as possible and not be 100% correct. Now the problem becomes maybe I have clicked on that. So okay. So now before I go to the exact problem and try to kind of say how you can address it, how we're trying to address it, and let's look at the complexity of problem even more. Okay. So now the problem is here that you are actually training a system where you don't know what kind of data you're going to process. Okay. So this is basically called kind of training process. Now challenges is there basically you have a various issues the data. One is that from the source itself, you are still learning about the feature of the source. So feature fixation is actually one issue. And the second issue that there is a data has various kinds of structural issues. The data is also like corrupted by various kind of interference problems. Is a basically man-made interference problem which is there in the telescope because of a mobile phone or various industry, everything. They add up to various kind of artificial signals which are nothing to do with the celestial sky. So those we call radio frequency interference. So they also introduce a various kind of structural issue in the data. So now how you basically address this problem? You learn as you go. Basically, it's a kind of data streaming learning problem. And now in that case, the thing is that when you learn something, you find that your learning is kind of drifting very fast. So your concept is kind of drifting, and you have to adapt to the drifting concept. Now I'll just show you this kind of some kind of show the complexity some sense. Like it is a pulse profile. There's a lot of pulse profile you can say. It's a real pulse profile. And if we put a sine curve and sine square curve on that pulse profile, and then look for the chi-square of these two. Okay, now this is sine curve and sine square curve is basically telling you how the pulse profile should be. And if you say that our match filtering or our convolution done correctly, then you should see these two actually. You expecting this are actually mismatched from this will get distinguished from your interference problem. So these are actually gray are actually non-pulsar. They are artificial sources which are introduced into the simulation, and the red one are the real sources. Now you see the difference when you zoom it. You see the distance between these two. Now, how you distinguish? Because they're looking like very close and very closely kind of sitting together. In this reference frame, we may not be able to distinguish it, so we have to look in a different feature space. Okay, that is why that is a complexity of problem, because only on the profile shape phase, you will not be able to distinguish between these two problems because they are very well connected. If you go to the higher parts, usually like when the chi-square increases, you are looking for a very bright signal. Definitely, if you are looking for a very bright signal in the sky, then your local interference is not a major problem. But when you're only looking for a very bright sky, that means you are missing maybe a large percentage of your discovery potential. So you wanted to actually work efficiently over the full parameter space, but it looks like a difficult. But anyway, I think you have already gone through this thing. So AI is something which is basically broadly collect everything is saying that you are actually making a system which is basically artificially programmed. And when you look at the various subset of AI, you look at machine learning is something which you are not explicitly programmed for, is learning on its own as the name says. But deep learning is actually a complex part of machine learning. It's basically like a human brain itself. It's basically a neural net when the problem complexity increases, and basically you have a large parameter space, and at that point we employ deep learning. So we have both of them. Depending upon where we are actually employing the problem, when you actually look for something like that, you have to go to multi-dimensional space, and at that point, you employ the deep learning. So now, okay, so I'll show you this problem in a different phase. So now, like there are three sources, one from the real FRB. So this, okay, so this is a pulse, and then how they are looking at frequency versus time, and how they are looking at the dispersion measure versus time. So as you are changing the dispersion measure, your signal time delay has changed, because I have shown in the cartoon in the detection plot, signal get delayed, overcorrected, undercorrected. So that will create a bow tie kind of structure. You can see the bow tie kind of structure. Now this is actually a real FRB, and this is actually the radio frequency interference. This is like a pulse. Now clearly this saying that, which actually I illustrated in the previous case, that based on this I cannot differentiate, because this looks like all of them same. If I have these two added, they here also I cannot differentiate much, because they are also in frequency versus time. Things look very similar. Only this is the kind of features where actually things look different. Though there is a challenge here to here, but still you can differentiate between these two sources. RFI kind of standing out differently. So why that is happening? Because it is a local source. No? So when the RFI is coming from the local environment, it doesn't have a dispersion layer, because there is no distance. So now they are all coming back to the zero dispersion layer. So that's why the curve, the bow tie center actually goes all the way up to zero dispersion. Okay, and then the curve becomes very straight. Now, if you are trained based on this kind of curve, then that trend algorithm, or the deep learning algorithm, will throw out this thing. It will actually put them at the level 0 because the binding classifier. But you'll actually put this also as a level 1. But you see the difference between these two. This is actually heavily inclined, this is less inclined, because there's a galactic origin, this is extragalactic origin. And as the source becomes extragalactic origin, the inclination increases. Okay, so if you go into the if you're going to very distant source, then it becomes almost horizontal. Then it's also give you another problem, because your bow tie is not visible anymore. So you have a sweet spot in this kind of, when you actually see the bow tie structure, it's going from galactic scale to extragalactic scale. But when you're really far away, like over a jet shift of 1 or something, then it becomes completely flat. Or you are operating at a very low frequency, either of that. So basically, and that is what the challenge is to us, because you are operating from 300 megahertz to 50 megahertz, is a very wide frequency range. And you know this curve is going to change drastically based on the frequency what you are working on, and based on the effort which you are going to find, based on the distance to the source. So that is challenges. But that is why not the nature is stopping. Nature goes ahead and said, okay, now you are training based on this kind of structure. I'll actually throw different challenges. I'll say that this is not a broadband anymore. So the initial thing which you thought the signals are broadband is no longer there. Signals these are all real FRB, and you can see they are actually has a very band limited emission. Now your training becomes even more difficult. Now you actually have to want to find this kind of source as well as this kind of support. So some of the FRB are broadband, some of them are band limited, right? So you actually have to have different kind of population in your training set, so that you are not really fooled by this. You can see this is a flat thing, this is a very high FRB. So I start this FRB. So now you just see that when I'm talking about the previous thing, as I move to the subject, I find there's various kind of difficulty we are facing. But one thing actually helping us, because we say that it's a large number of beams, so it's almost like 2,000 beam source, 2,000 beams in the sky. So basically helping us to have a multiple eye on the sky. And when you have multiple eye on the sky, then the good thing is that the FRB will mostly come up in the very few eye, or very few beam. But where the radio frequency interference comes through various beams. So there is a possibility, and what we are right now doing is called density-based spatial clustering, which is called DB-scan. And that is actually working out quite efficiently now to distinguish the spurious detection, which is basically radio frequency interference mostly, compared to real event when you look at the multi-dimensional parameter space. So now this is just giving whatever I talk to you, this is giving you different how the signals are moving. It's not that much important. Maybe I'll go to the last slide and I'll talk about the different part of that, and I'll stop here itself. So now here you see that there's three different, I already gone through each of these cases, but now I'm putting the explicit technological term, what you're going to work, what you are working on. So basically like the deep learning classifier, which you're building to classify those various kind of bow tie structure and different kind of inclination angles that need to be very fast, because it make a decision, million candidates per minute, which you have to make a decision based on those kind of data rate. So that is based on something called tensor IT. So everything is implemented inside GPU. So GPU is called graphical processing unit, is very fast, and that is the only where you can get a real-time scoping. So that is tensor IT is something you don't have to worry about it, but you can actually appreciate this fact that we move all the way from 32-bit floating point to integer 8. Because then if we are operating on lower integer, lower sample width, we are making decision very fast. you compromise on accuracy, but it's fine. The decision problem is a 1 and 0. It's not, it's a binary classifier. With a binary classifier, you can actually compromise on the accuracy because you have to just make 1 and 0. And the second thing which I already talked about, there is a density-based spatial clustering is happening, which basically try to distinguish between RFI and FRB by using multiple eye on the sky. And then the last thing is actually also important, how to kind of build all the structure, extract all the features, which is basically you want to do it. So that is also, so there are 3 different forms, which you combine all of them together, then you find the actual AI getting implemented. So that is why all the students are working on. I have just highlighted their name, give them credit on this. So I just summarize here. So if you do everything correctly, if you really are able to kind of classify million candidates per minute properly and try to bring out the real sources from there, then you basically can see a high impact science coming out from the GMRT. And that means we have to address all the questions which I have kind of posed to me. I don't have answer to all of them, but I see the problem and it's kind of getting complex day by day because of the RFI as well as we are understanding more and more of the source nature. That's it. Thank you.
I have one. So, how do you create the training data? Is this based on some known events that you use, or you are trying to put in certain profiles and then simulate anything?
Yeah, I think this is very important thing actually, how to create that training data set because of this the features as well as source as well as RFI. So initially we started with having kind of simulated thing, but now you realize the simulated means is basically it is biasing your own decision. So the way right now we are doing, you have a real-time simulated pulse only. It's a real-time injection in the GMRT. So basically when the signals come from the GMRT, which has all kind of RFI mark setting in the data, it's a real information going to post, we inject only the pulse in that. So we only inject a pulse shape and then the dispersion measure on event on that. So, and they are also put various kind of complexity in that, but the noise is kind of real. In that real injection space, you are actually doing the training. So that kind of help us. It's not fully 100% real. Yeah.
Other questions?
They're able to able to predict
is able to find the funding. So I'm saying that whatever the final thing what you're talking about, the million candidates per minute, that is what you have not, this is a prediction, you have not faced that, you have not gone to that parameter space. But whatever the limited parameter space you are working on is actually finding event. Right now we have control system, you have to inject something in the real data and see whether that injected thing comes up. You actually change the intensity of the event, that means the brightness of the event, you space the event at different distances. Those things are working out, but I can completely say it will not work out tomorrow because the complexity will change, the telescope environment will change, and our algorithm may fail. So it's something which is say working today, but it's not that is 100% confidence that it is working like in the change environment tomorrow.
So are there FRBs detected right now?
We don't know. We don't have any real FRB ratings. Only the repeating FRB which I say, because those are something which you know. There are one particular FRB which is periodic in nature. That is getting detected day and day. So you basically know where to look for it because then you get it. But there's unknown FRB is not because we have not tried the unknown FRB yet in that multi-parameter space. Yeah.
So the RFI classification and segmentation, do you think that can also be applied to the regular GMRT observation? So is there a plan or thought process for taking information from the new correlator, there is a correlator, and then applying it to GWB data?
That's possible, especially the third one which I'm saying that is basically looking at the hydrometry dynamic spectrum. Yeah. That's possible because you can actually get the mask out of that and you can apply on the data. Because that is not changing drastically dynamically, it's just staying over that dynamic spectrum. But looking on a time series, we may not be able to do because these two are not very aligned in terms of time. But in dynamic spectrum level, definitely you can do. I agree.
The screen sharing. So thanks, Jim.
Thank you.
Okay, so next we'll learn about machine learning applications to gravitational wave data.
Hello, hello. I hope everyone can hear me. Can you hear me? Hello? Okay. So let me begin by first. Yeah. So as we mentioned, I'm going to talk about machine learning applications to gravitational data. I'm going to present this in a very broad manner, so that you get a sense of what sort of applications are, what sort of ways these applications are happening for the gravitational data. Right. So these various gravitational sources that we have been seeing from the global observatories, these are mainly these compact binary coalescence kind of systems. So these are merging binaries of either comprising of binary black holes, binary neutron stars, or a neutron star black hole. So they tend to have these characteristic waveform where you see the in-spiral, the signal from the in-spiral, eventually the binaries, they merge and followed by a ring down of the system, where you see the final remnant. So this is the kind of time series signal that you can see in the gravitational wave data. So here I'm showing you examples of the real gravitational wave events that have been found from the LIGO and Virgo collaborations. And on the left hand side of these panels, what you are seeing are the time frequency spectrograms, where you can see these characteristic chirping like profiles of these sources. So these CVC kind of gravitational sources, they can be defined by a bunch of physical parameters and some source dependent, the detector dependent parameters. So the intrinsic parameters are typically the masses and the spin, and the extrinsic parameters are, for example, the sky position, the distance of the binary, the orientation, phase, and so on. So these set of parameters, both the intrinsic and the extrinsic parameters together, allow us to exactly predict how the gravitational wave signal will look like. In principle, the gravitational wave emission is expected to arise from different types of sources. So I have here shown different examples of the right now known gravitational wave sources. So they fall into the category of, let's say, the short duration versus the long duration. On this side, they fall under the category of waveforms which can be easily modeled with the help of few parameters, like how I showed for the merging binaries, or these could be unmodeled kind of waveforms where we don't really know how the profile is going to be. So there are different, as I said, there are different kinds of expected gravitational wave sources, but there could also be unknown types of GW sources. And a lot of the work is going around in terms of detecting these different types of gravitational wave sources. Most of the work is happening in this area because these are the kind of events that we have been finding in our observatories so far. But there is a lot of work happening also in developing algorithms for identifying different types of gravitational signals. So let me motivate why we need machine learning in addition to the existing algorithms, in addition to the conventional algorithms for in this particular area of gravitational waves. So there are different reasons for this. Firstly, gravitational wave signals, they are like a needle in a haystack, and the data that we observe, it consists of a lot of non-Gaussian transient noise features, which are called glitches. So a lot of work actually goes into reducing these glitches which are found in the data in an abundant manner. And also there is a big data challenge in gravitational wave data, because in addition to the main science channel where we see the signal, there are many other auxiliary channels which are continuously monitoring the detector, the health of the interferometer, and so on. And there is a lot of information in there which can help us understand the origin of these glitches, and which can then also help us to get rid of these glitches, and this just helps us improve the detection of the main astrophysical gravitational wave signals that we are interested in. So, it's very important to be able to analyze these auxiliary channels in an efficient and fast manner. Next is we need to be able to do rapid search as well as parameter estimation of these gravitational wave signals, because this can be extremely useful for the multi-messenger science. In this case, what happens is that if you see a gravitational wave signal, you want to be able to rapidly send alerts to the rest of the astronomy community so that we can follow up these with different telescopes, like either in the optical or X-rays and so on, to be able to catch the counterpart of these gravitational source. So, and then lastly, there are these conventional methods may only be able to find certain kind of gravitational wave signal, which we have understood and can characterize very well, but there can be some unmodeled or unknown sources of gravitational waves, which may not be, which our methods, conventional methods may not be able to catch. So for all these various sorts of reasons, we need machine learning so that we can improve our ability to detect these signals and study them. So let me just give a summary of the different types of input data people have been using for the analysis using machine learning. Primarily, we are looking at time series signals. So there are various works that have made use of the time series signal directly, but there are other ways of also analyzing the gravitational wave signal data. For example, you can generate these images on maps, like I showed you earlier, the time frequency spectrograms, where you can see this chirp-like profile. So you could have a time frequency spectrogram, or there are these other formats where you can again take the gravitational wave signal and then project it into different, using different transforms, and generate something called CWT scalograms or sign Gaussian prediction maps and so on. There are also some studies which make use of video streams where again these video streams are again coming from the case situations where they are monitoring the interferometer and the state of the interferometer, and it helps us to understand, better understand what is happening, whether there are some problems, whether there are some issues, and one can then use these video streams to analyze and prevent these kind of disturbances from happening, or make some sort of early predictions for what is going wrong with the system. And so, talking about the different machine learning techniques and how they are then applied to the gravitational wave data. So the standard, as you know, the standard techniques that are used in machine learning, these fall into these various categories. For example, either you are looking at a classification problem or a regression, or you can use machine learning for denoising your data. There's also something called as predictive maintenance, which allows you to make early predictions for some sort of failure happening in your detectors. So let me just quickly give examples for each of these types. So in these classification problem, typically we are looking either for detecting the CBC signals, which are like binary black holes and so on, or it could be mitigating the noise from arising from different glitches. Next, we could, for the regression problem, we would be interested in making predictions for the various parameters that define these binary black holes. For example, the masses, spins, eccentricity, and the sky localization. For denoising, of course, we want to try to minimize the noise that we are seeing in the data. This is not the, I'm not referring to the glitches here. I'm just talking about the ambient noise or the background noise that is there in the data. It allows us to enhance the detection of the gravitational wave signals. And lastly, as I mentioned, for the predictive maintenance, it's these kind of algorithms then allow you to make predictions for your detector components by monitoring the detector performance over a long period of time to be able to then say when that particular detector component might undergo certain failures. So let me, from the next few slides, let me give an overview of the different works that are happening in the literature for each of these different types of machine learning techniques that I just mentioned. So I'm just going to give a quick overview and go through various applications. So firstly, this is about identifying and eliminating glitches. So as I mentioned, in the gravitational data, we tend to see a large number of glitches of different types. So here I'm showing again time frequency spectrograms where you can see these different morphologies of arising due to different types of glitches. In this particular study, they try to look at the auxiliary channels which could show some correlations with these glitches which are seen in the main science channel. And so in this work, they have tried to parameterize the data in the auxiliary channels, and in these in these different columns, they are looking at different machine learning algorithms and comparing their performances. And so here in the upper panel, they have tried to look at the variation in the different parameters that define those features in the auxiliary channels. And in the bottom one, they are looking at what if we reduce the number of channels and only focus on some of the significant channels, then what effect it has. So overall, what they find in this work is that by looking at these different types of machine learning algorithms, they are able to find comparable performance, and there are only certain parameters which are more important than the other. And what they have concluded is that right now the existing conventional algorithms are already able to very efficiently identify the glitches, and we need to be able to make use of some different kind of data to be able to further make improvements in these identification and elimination process. Next, I want to talk about a very different kind of approach which has been used for characterizing glitches. As I said, characterizing glitches is one of the very important tasks in the whole analysis framework in the LIGO-Virgo collaboration, because these glitches are abundant and they arise from different phenomena, and many of the phenomena are not understood, and their correlations in different auxiliary channels are not understood, and so on. So this is a massive project, and the idea behind this project is to combine machine learning with citizen science. In citizen science, what happens is that you show data to on a website, and it is open to everyone all over the world, and people, or in this case, it's called a citizen scientist who can access that data and help you to analyze and process this data to answer a certain scientific question. So in this case, what the way this project works is that at the first step, there is a machine learning classifier that initially goes through the various triggers that come from the data, or generates its own triggers from the data, which obviously correspond to lots of glitches, and all these glitches are then passed on to the citizen science framework, where the citizen scientists will go through these images and then classify them into different types of glitches. All these new classifications that will come out, if they are very confident classifications, then they are fed back to the original training set. Any sort of uncertain classifications are then further analyzed by the experts, and then they are further fed back to the training set to create a revised training set for the machine learning algorithms. And this way, this process continues to provide better classification of these glitches, and sometimes even we come up with new categories of glitches which were not known before. So just a very quick snapshot of how the data looks like. The way the data that is used in this project is that for a given timestamp, they look at 4 different time segments of increasing time window, and these 4 different images are provided to the entire framework. So for the machine learning part, they had considered 2 different ways of analyzing this, either a parallel view where you analyze each of these 4 images separately and then combine them, or you combine them initially and then go through the single sort of, network. And overall, they find that this merged view seems to be performing much better. And here I want to just quickly show some of the more conventional searches that are happening for searching CBC kind of signals, primarily the binary black holes with CNNs. So this is making use of the time series and injected in different kinds of Gaussian noise, and looking at the performance of the conventional, conventional convolutional neural network. And then here we are looking at these ROC curves where we can see the true positive rate versus the false positive rate to determine how the networks are performing in different, where the signal is injected in different SNRs. And then it is also compared with some of the conventional non-machine learning based methods. In the bottom here, this is another study which further allows you to distinguish the different types of CBC sources. So from the binary black holes to binary neutron stars to the NSBH. So in this work, they have attempted to distinguish if you have a data segment, then can you identify whether you are looking at a binary black hole or a BNS or an NSBH, or is it just some noise? So here they have also shown results on some real events, which seems to perform better in most cases. In this particular case, we are looking at BBH versus glitches. So we want to discriminate a data segment that may contain a glitch from actual BBH. So here we are making a novel way of creating the input data, which I also had mentioned earlier. So here we are taking the signal and cross-correlating with sine Gaussian function, and then in the end we generate a map which is defined by the parameters of the sine Gaussian instead of the standard time frequency map. Here we are looking at the parameters of the sine Gaussian function itself, and here the whitish pixel show the strong correlation with the sine Gaussian parameters given by the Q, which is the quality factor, and F naught, which is the central frequency. And here we can see on the left hand side, this is how the projections look like for a BBH, for a genuine gravitational wave source, and here how it looks like for one particular type of glitch. And with the help of these kind of images, when we look at multi-detector data, we are able to come up with a CNN algorithm which can very efficiently make a distinction between these. And then this is also applied to the real events, and we are able to get 95% accuracy on the real events using this different type of projection maps. Next, I will talk about the denoising applications. So there are some studies in which the denoising is applied to the time series signal itself. And so here we can see in these different panels, so this is the original data, and this is the denoise signal along with some uncertainty plotted in the shaded region. In this work, they have simulated several these BBH signals, and then in the result, they are showing how what is the recovered SNR from their denoise signal as compared to the injected SNR. And the darker colors here show that there is a good overlap between the injected signal and the denoise signal, and you can see this one-to-one correlation between the injected and the recovered SNR. And this seems to work well in many cases. And another way of denoising that people have tried to apply is instead of actually denoising the rest of the pixels where there is noise, instead of that you can use something like these kind of autoencoders where where you're actually just picking out the signal itself and ignoring the rest of the pixels. So these maps are similar to so these maps are actually the continuous wavelet transforms. And here again, you can see this similar chirping binary profile And but here this is the test data where you can see all these noisy pixels, and after running it through this autoencoder, you're able to only extract the signal. That way you are able to enhance the SNR of your signal, and these profiles you can then compare with the original signals for the same parameters. So in this work, then they have made use of this very efficiently to denoise their signals, and then later on combined with some other machine learning methods, they have tried to improve the detection of binary black holes. So talking about the parameter estimation, so in this work, they have looked at the making use of something called the Bayesian neural network to make predictions for some of the intrinsic parameters of the binary black hole. For example, the masses and the spin and some parameters corresponding to the ring down of the signal. So in this work, with the help of these Bayesian neural network, they are able to get decent constraints on these parameters. They have made use of some different kinds of algorithm here, not the conventional neural networks, but so you can look at this, and here they are able to successfully predict the model parameters for the BVH waveforms, but they still have to analyze BNSs and NSBH, which tend to have longer signals, and that can be much more time consuming and much more challenging. Next is the parameter estimation done for some other, so this is using some other methods. So here they are using again autoencoders for making model parameter predictions. In this particular approach, they have shown how well they can do the model parameter prediction and how comparable it is to some of the conventional methods which use NCNC. And as you know, the NCNC methods, they are extremely time consuming. And so with the help of this kind of framework, you're able to make predictions for these parameters in a matter of few minutes or so, or even less than that. And they have shown here in comparison with some of these conventional methods that the accuracy that they achieve in these parameters is comparable. Just lastly, I want to show that there are some studies which do not care about the intrinsic BVH parameters, but are only focusing on localizing the source in the sky rapidly. This is extremely important, as I was saying, for the multi-messenger science, so that you can rapidly follow once the candidate is identified, you can rapidly follow up with other telescopes all over the world. So in this work, they have come up with this artificial neural network, which in which way they divide this sky into different sectors, and they have studied how by increasing the number of sectors, how well they are able to identify the direction of the source in the sky, and what sort of other challenges they face compared to the conventional methods. So, but you know, under some limitations, they are able to get comparable or better performance and within a much shorter time frame compared to the rest of the conventional methods that are used for sky localization. So in summary, LIGO presents many big data challenges, and data mining tools are highly valuable here. I talked about different machine learning techniques that have been used or are being used currently for problems related to the detectors, search methods, and even to study the astrophysics of these signals. So machine learning expertise is extremely important. It is very much required. I didn't really talk about LIGO India specifically, but as you know, LIGO India is approved, and many of us are working on LIGO India, and we would like to have many new people, young people like you, who would help us with these machine learning problems, and you know, make use of these new data that we get to be able to give better constraints and improve performance for gravitational wave detection. So thank you.
Yeah.
you mentioned localization with element, so how fast is it compared to, let's say, so you mentioned base star, compared to base star, how much of a gain do you expect?
So this was more of a feasibility study that they did. So here they have mentioned that they take about 10 seconds or so, 10 seconds to 1 minute, which is much faster than some of the other algorithms.
And like, so do you like overestimate the let's say calculation area compared to, let's say, full parameter estimation, or do you have an underestimate of the area?
So here, the few test cases that they have shown, the uncertainty region that you're seeing is still like a few hundred square degrees, which is again comparable. So, right. But the thing is that in this work, this was like a first feasibility test that they did, and they are looking into improving their algorithms. With this analysis, this is the sort of accuracy that they get, and it is comparable. It's not worse or better.
In the regression model, you mentioned that eccentricity, through eccentricity, we can estimate properties of black holes. So, can you elaborate on in that slide you have mentioned classification, regression, denoising, and
yeah. Yes.
In this, in the regression, one properties of
yeah, the eccentricity corresponds to the eccentricity of the orbit itself. So, what is your question?
So means how that plays roles in estimating the parameters of a particular.
Eccentricity is one of the parameters of the DDH signal. And so there could be if you are looking at this gravitational signal, then systems which do not have eccentricity versus the ones they do, those signals look different. The morphology or the shape of those signals look different, and so you can develop algorithms. There are already works where they have devised algorithms where you can look at the time frequency spectrograms, for example. Which were shown here like this. Here, you can look at these kind of time frequency spectrograms. They show different morphology for the eccentric versus non-eccentric signals. So, with the help of analyzing these kind of data, you can at least do a crude division of whether the signal is highly eccentric or moderately eccentric or not so eccentric.
Yeah. So there was this other study which is outside of LIGO, who are also searching for these mergers in the LIGO data, this method, etc.
Yeah.
So they also typically use, I think, machine learning to data mine these things.
I don't think so. I think, they may have used in some subsequent thing, but the original work that they did in order to improve it was to be able to get rid of or minimize the noise using some other method, and that's how they managed to improve the detection of the original signals and detect some other signals which were not reported. I don't think it was machine learning.
It was not based on machine learning. Okay. I think just yesterday or day before yesterday they published that they found 15 new candidates.
Okay.
I don't know. Yeah. So I don't know what you guys think about that.
Maybe we can continue over the debate and then because there's still more talks to go. Yeah.
No, I can do it from there.
You can?
Yeah.
Yeah,
What's coming on the, see, this might be coming on the Zoom.
no.
The slides I can see on
The slides you can see.
same
one.
slide I can see. This one, right? Not my screen.
No, the whole screen is shared.
Yeah.
Yeah,
That's what you want, right? Yeah. Okay.
now.
Yes. So Yogesh will tell us about deep learning studies for Galaxy.
So I changed the title from what's announced on the program a little bit, but I think this is more appropriate. So yesterday we encountered some terms, jargon from machine learning. So I'm not going to repeat that or explain that again, but I hope I've listed them here just so that you can quickly review and make sure you understand what all of these concepts mean. So various people have said why machine learning is needed in their domain, and I'm going to say why machine learning is needed in the area of large astronomical surveys. Large astronomical surveys are producing vast amounts of data today. We are drowning in a tsunami of data, but the number of astronomers are growing slowly while the data are growing exponentially. And these large area surveys are producing data of excellent and uniform quality. A great deal of effort has been invested in making the data what are called fair. Fair means the data should be findable, it should be accessible, it should be interoperable, and it should be reproducible. And if all of these things are there, you turn the data to be fair, and that makes optimal utilization of the data possible. At the same time, over the last few decades, the enormous increase in compute power of computers has meant that machine learning and AI techniques in general are becoming ever more capable day by day. And I don't need to provide you with examples. And they're now becoming increasingly capable of working on tasks that were the exclusive reserve of humans until recently. Deep learning techniques, which are a special case of machine learning, work well on problems involving both classification as well as regression. Regression, remember, one means prediction of quantities that are continuous, such as redshift, star formation rate, and so on. So this increased importance of AI and machine learning in the field of astronomy as in other fields is reflected in the rapid increase in the number of refereed papers in astronomy over the last 2 decades. And you can see that's clearly an exponential. I started with the year 2002 because that's when I wrote my first paper in the field. Ajit mentioned that paper yesterday in his talk. At that year in 2002, there were a total of 14 papers which were on machine learning in general across all of astronomy. And in 2021, there were 820. So in those days, we used to know all the people, all the astronomers who worked in this field. Now, of course, it's exploded. Is this because the number of papers in astronomy are growing exponentially? No. This is the total number of refereed papers in all astronomy journals over the same period of time. And you can see it has gone up sort of linearly from about 20,000 to about 35,000 in 20 years. So the fraction of machine learning papers have gone from a number very close to 0 to about 2.5%. And this data is from 2 years ago. I think I have to redo these figures to make them more correct. If you fit an exponential to this curve, it fits nicely. And you get a doubling time of about 2 years. So every 2 years, the number of machine learning papers in the astronomical literature is doubling. So yesterday we saw in Ajit's talk what a simple neural network looks like. The one on the left, where there is one input layer, one hidden layer, and one output layer. But in deep learning neural networks, what you do is that you simply increase the number of hidden layers in the network. And of course, this is not a very dramatically new idea, but it became possible to use deep learning neural networks only in the last decade or so, when computers became powerful enough for them to be able to compute the weights of thousands and thousands of interconnects that you have in these within these hidden layers, and to do it in a finite amount of time. So the deep learning came into its own as a practical idea only in the last decade, although theoretically it had been formulated many years previously. In any machine learning process, this kind of training and inference process is quite similar. You take a training set. If you're doing supervised learning, then that would be a labeled training set. And you use that to train your model. And once your model is trained, it can be used for prediction. And it can then, you give it, say, a photograph of a cat, and then it will hopefully correctly give you output label as cat. And in classification problems in astronomy, people have done this sort of thing with various kinds of things. I'm going to talk about classification of radio galaxies in a minute. But people have taken, for example, optical images of elliptical galaxies, lenticular galaxies, spiral galaxies, etc., and asked the machine to classify these properly. There's been a lot of growing interest in this field within the last few years. So what I did was in 2021, I just took these 800 odd papers that were there, and I just went through the first authors of all of those papers and checked how many of them have an Indian affiliation. So we had 47 papers out of 824 worldwide, which were written by authors working at an Indian institution. And these are just some of those 47 papers, the titles of those papers. And you can see readily that it's sort of all over the place. So a wide variety of domains in astronomy are now using AI and ML techniques for all kinds of problems. So I have worked on 3 specific problems using deep learning. The first one is the classification of radio galaxies into different classes. This was done using very old data from the first radio survey. The second project that I worked on involved the prediction of star formation properties of galaxies, just given their UV, optical, and infrared flux measurements. And the third problem was to predict the bulge to total luminosity ratio of galaxies using deep learning. So what was common amongst all of these 3 research projects was the fact that we used deep learning in all of them. What was different, of course, is that the first one was a classification problem, and the other 2 were predicting continuous values. They were regression problems. So today I'm just going to talk about the first 2 problems, one a classification problem and one a regression problem. Another thing I want to highlight is that this is a young people's game. So these are all my collaborators on the projects on these 3 projects, and their average age at that time was about 23. So this is really a young people's game. So let's look at the first problem where we want to predict the star formation properties of galaxies. So suppose I show you this nighttime photograph of our country and ask you to determine, using this photograph, what is the population density in different parts of the country, right? So if you made a very trivially simplistic assumption that light is directly proportional to the population density, you would be able to make a density map. However, that's not true. Urban areas and rural areas produce different amounts of light per capita. Similarly, rich people and poor people also produce different amounts of light per capita, and so on. So if you could model all of these factors into your model, then you could construct a population density map of the country. For galaxies, we want to do something similar. So this is an ultraviolet image of the Andromeda galaxy. And what we would like to do is we would like to do for the galaxy as a whole, and in some cases for parts of the galaxy as well, we would like to know how many stars there are and whether there are young stars and old stars, and so on. So in order to do that, you need to model various things. So for example, you need to know what is the initial mass function of the stars, which means when stars are born in a open star cluster, what is the mass distribution of the stars when they are born. And then you need to, of course, know how stars evolve. Okay, how do they evolve on the main sequence of stars, and outside it, how much time do they spend in each phase, main sequence, red giant, white dwarfs, etc. You'd also need a spectral library, because that, which will be a function of metallicity, that will tell you what is the spectrum of a particular type of star as a function of its age, mass, and metallicity. Okay? And then, of course, you need one last parameter, which is what is called as the star formation history, which tells you how many stars formed at different points in time over the entire lifetime of the galaxy. And in addition, the last thing that you need is you need some model for the dust attenuation, because there is dust within the galaxy itself, there is dust in our own galaxy, etc. And all of this dust will change the spectrum of that galaxy in a very systematic way. So you need to have some dust model that tell you how that exactly how that happens. And then if you do that, then you can use what are called stellar population synthesis models to fit the data. So what you see, the blue points that you see over here are actual flux measurements made in various bands going all the way from the galaxy UV filters all the way, I think in this case, to the far infrared and even the radio. And so if you did all of this and you did the stellar population synthesis modeling correctly, you will get a red curve of the kind that you see here, which represents a physical model of the galaxy, which takes into account the effects of the star formation history, the dust, the IMF, etc. Now what we want to do is we want to do the same thing, but without involving the complex astrophysics of stellar population synthesis. Okay? We want to do this whole process, we want to replace the stellar population synthesis model with a machine learning black box. Where it will take the same inputs as the stellar population synthesis model, and give you the same outputs, but it has no knowledge whatsoever of the underlying astrophysics. So the inputs are the same. These are broadband fluxes in the UV optical infrared bands. And the outputs that we try to reproduce are the star formation rate, the stellar mass, and the dust luminosity. The data for this training and test sets that we used came from a very large survey that was carried out over the last decade or so, which is called Gamma. And we only use galaxies more massive than 10⁹ solar masses and at relatively low redshifts. Nevertheless, we had about 76,000 galaxies in our training plus test sample. And what are the true parameters for each galaxy? These have already been determined for us in a paper published in 2016 using a stellar population synthesis code called MACFIS, which tells you what is the stellar mass, what is the star formation rate, etc. So those we take as the true value. And the deep learning network was constructed using Keras, which, as you heard yesterday from Asitan, is something that sits on top of TensorFlow. And this work was led by a data scientist from a software company who was working with us. This lady, Shraddha Surana, she designed the network. So this is the table, which these two tables describe the network. In some parts of the configuration were different. So we generated 3 separate networks. We ran a network, designed a network to predict stellar mass. We designed a different network to predict the star formation rate and the dust luminosity. And of course, some of them had all of these 3 models, deep learning models, had the same configuration, common configuration as listed in the table below. So here's the stellar mass prediction. So focus on the panel below. That tells you how much the scatter is. The RMS error in this case is about 0.05 dex. Remember, it's a log scale there, the y-axis, and on the x-axis as well. And you can see that there is scatter, but the scatter seems to be relatively uniform on both sides. And the scatter is not very large as envisaged, as given by the RMS error over here. You can do the same thing for the star formation rate prediction. Here now the RMS error is somewhat larger, but again the systematics are relatively small. The scatter seems to be random, although larger. So what you have there, the dashed line is actually the best fit to the data, and that zero line is ideally what you would have if you had zero systematics. This is for the dust luminosity. Here the RMS scatter is now somewhat lower again, but not as low as what we had for the stellar mass. So now you should notice the following. First, there are few catastrophic outliers and very little systematic error in the prediction. But we must remember that we are learning the behavior of the stellar population synthesis code, not of the real universe. Okay? So if the SPS code is deficient in some part of its modeling and is giving you wrong answers, then the deep learning code will also learn those wrong answers and give you the same answers. But the main advantage is speed, and that is a tremendous advantage. A trained network took less than a second to classify 10,000 galaxies on a laptop. Okay? Whereas if we ran the SPS code, it would take several weeks on a multi-core desktop for the same number of galaxies. So the second problem that I want to mention is the classification of radio sources. So radio sources, radio galaxies in particular, come in two kinds of flavors. So first is what are called FR1 galaxies, which are quite bright near the center, and they fade away towards the two lobes. Contrastingly, the FR2 galaxies are faint near the center, and they have bright lobes. Then there is a third category of radio galaxy, which is what we call compact, which does not have these well-defined lobes and has a single block of emission. Then the fourth category that we have is what are called bent tail galaxies, and these are typically galaxies that are moving through a dense medium like a cluster, and therefore their lobes sort of bend over to one side, and these are the bent tail galaxies. So what we said was, let's give it, we had a labeled catalog of these 3-4 objects, which we had to augment by rotating and things like that. Let's try and classify these galaxies into 4 categories. And for this, we used a different kind of network. It's called DenseNet. Specifically, DenseNet 161 was the one that was used. And again, this was a project led by an undergraduate student, and he spent a tremendous amount of time constructing this DenseNet network. And this table basically describes to you what is the configuration of the various hidden layers within the network. And this was not done using Keras. This one was done using PyTorch. And I actually wanted this also to be an exercise in trying to see which of these codes are more suitable for our requirements. And therefore, we use different technologies for different projects. So we achieved a 92% accuracy in this 4 category classification. Most of the failures, and here you see some of the failures that we had, are confusions between bent tail and FR2 galaxies. So this, for example, is the prediction is that it's bent, but actually it's not bent, it's an FR2. On the other hand, this one is actually an FR1, but is predicted to be bent. So there are a number of limitations of these kind of techniques. So first of all, the biggest one is small and biased labeled datasets. Perhaps one can use citizen science projects for this purpose, We already saw an example from Anuprita where they're trying to do that for gravitational waves. Unbalanced training sets lead to false positives for rare objects. So this is a very, very real problem. Uncertainty needs to be quantified. So possible solution would be some kind of Bayesian approach. Interpretability, Ashish spoke about that, this black box effect, you don't know what's going on. Sometimes we do domain shift, which means we train on simulations and run on real data, and not exactly clear how well that works. And benchmarking and scaling, of course, is very important. And how we compare different approaches and how we scale them to petascale is the real challenge. Petascale is a challenge for the future generation of radio telescopes like this. So there was a recent review article which basically talked about the application of ML techniques to galaxies and cosmology in general. And these are the things that have been tried out, convolutional neural networks, and PNNs, RNNs, and so on. So there is a lot of space for experimentation. There are a lot of missing tick marks there that we can work on. So if you want to know more, this is the review, Impact of Deep Learning for the Analysis of Galaxy Surveys. It's an excellent review by Huertas Company and Lanus. Gives a very, very broad overview of what has been happening in the last decade in this field. So I'm going to stop here and take your questions. But before I end, I've put up this slide. This is particularly relevant for those of you who are in your pre-final MSc year and are going to do MSc final year next year. Of course, BS, MS students are also included. We have an Indo-UK project that will support visits for 3 to 6 months duration to some of the top universities in the UK. And it's fully funded, travel, stay, everything. And remaining part of research thesis will be completed at NCRA. Besides me, Jayanto, I think we forgot to mention that. But Jayanto also has a project associated with this. So I know there are many ISER students in the audience, so please come and talk to me if you want.
Okay, thank you. Yes.
You mentioned that the machine learning model might be learning the deficiencies of, let's say, a particular synthesis code. Is it feasible to combine, let's say, results from different codes together and then train the machine learning algorithm on?
You could. See, what happens is that if you take 2 or 3 of the most popular codes, so we tried this experiment with using Seagal and Matfis. These are 2 of the popular codes. We found that except for some edge cases, these 2 codes are giving you the same answer. And they're giving you different answers in the edge cases. Maybe that will help you identify galaxies where you shouldn't try machine learning. I think that may be the good approach to take. That you only train on objects that are this. But of course, there, if you don't give machine learning examples and you have those things in the test case or in the real life situation, it won't work well.
So, yes.
The case where we are needing networks because we don't have data, then we can use our like unsupervised algorithms.
Yes. So unsupervised learning can be used in a few cases, but sometimes what happens is in the unsupervised learning, categories which are physically well defined can get mixed up. Okay, so FR1s and FR2s may overlap and things like that. So unsupervised learning is probably more suitable where you don't have well-defined categories from the astrophysics side. You don't know anything. It's just some numbers and you want to see patterns in the data. But where supervised learning works and works well, and right now doesn't work only because you don't have labeled data sets, it might be a better idea to get those data sets labeled and then proceed. So that's the approach that most people are taking.
Do you also get, apart from star formation, stellar mass and dust, do you also get metallicity as well?
Metallicity is quite degenerate. Okay, it correlates with other parameters like age, and also the variation of a particular spectrum for different metallicities is very small. So if the change is very small, it's very hard to determine. From broadband fluxes, it's virtually impossible. So you are better off just gathering a spectrum for those galaxies and then using the optical spectrum to get them.
Also, no work has been done with regard to metallicity.
Metallicity is harder, as I was just mentioning. With broadband fluxes, getting the metallicity is virtually impossible.
So I'm trying to ask, like, no one has done previously work with this, calculating metallicity.
Yes, and that is for a reason, because it's a really hard problem.
Not from fluxes.
Not from fluxes.
People,
From spectra, people have done. People have done using spectra, even classification of spectra. Is this a quasar spectrum? Is this a Seaford spectrum? All that has been.
One quick question regarding uncertainties. So you told us about MAPFIS. MAPFIS can in principle also output uncertainties and variances between these different uncertainties.
Yes, yes.
So is this also something that you try to train your network on?
No, we didn't. We didn't do that. Yeah, yeah. So you have, yeah, that is something, taking the errors into account properly is an important consideration. But AI ML techniques are a little deficient in that area because they've been trained on their high signal to noise kind of problems. They've worked classification of cats and dogs.
Okay, so maybe let's thank Yogesh now. So next we will hear about emulators for cosmological inference from our presentation.
Okay, so I'll talk about one very specific application of machine learning to cosmology, and that is in the form of emulators. So this is something Yogesh just mentioned, so it's a good segue. So data in cosmology comes in various forms and from different redshifts. So it could be the CMB at redshift of 1100, could be galaxy surveys, which typically peak at redshifts of say 0.5. It could be intermediate redshift CMB lensing, 21 centimeter. So apart from CMB, all of these are loosely termed as large-scale structure of the universe. I might use the term later on. And also the data comes in different forms. So for the CMB, it could be a sky map of temperature fluctuations. For galaxies, it could be a collection of points in 3D space or in 2D space, and so on. And what we're trying to do is we are trying to fit our favorite cosmological model to this data. We have various models for the evolution of the universe over this entire range of redshift, and then if you also for earlier redshifts. They predict the evolution not only of the background universe, but also of the fluctuations in the universe. The simplest model, which most of us typically use, is the lambda CDM model with an FLR2 metric. Seems to be a good fit to all the data, has roughly 6 to 10 parameters that relate to the boundary conditions. But now that we have all of this data at different redshifts, we can ask many different questions. First of all, we can ask how good is the model fit? If you trust your model, how precisely can we constrain the parameters from the data? If you analyze data from CMB at redshift 1100 and separately analyze galaxy data at redshift 0.5 with the same model, do you get the same parameters? Okay. So these are the sorts of questions that you can ask. Now, I also wanted to introduce the concept of summary statistics. So what typically happens in cosmological analysis is that if you're given the CMB temperature fluctuation map up there on the top, so every point is a pixel on the sky, and it tells you how the temperature is varying across those pixels. You do not try to analyze that map directly. What you try to do is you try to summarize what's happening in that map. Typically, what cosmologists do is look at what is called the two-point correlation function, or its Fourier or spherical harmonic transform, the power spectrum. So what is the two-point correlation function? So you look at this point on the sky and another point that is some fixed angular separation away. You look at how correlated the fluctuations are between those 2 points. Now, keeping the same scale, you average over all possible points on the sky. Then you pick a different scale, repeat the same procedure. So that's what the two-point correlation function is. If you take its spherical harmonic transform, you get this very beautiful picture from the CMB. This is the power spectrum of the CMB. So basically, you have summarized that entire map into these sets of data points from this plot. Okay. Now, we want to do parameter inference from whatever observability you have. So the analysis typically employs a Bayesian approach. So what we are trying to do is we are trying to come up with the posterior distribution of the parameter values given the data. To do that, we need two things. First of all, we need the prior, which sort of either comes from some previous experiment or some physical constraints and so on. But you also need the likelihood, which is the probability of getting that particular data given a particular set of parameters. And now you have to find the value of the likelihood at all possible points in parameter space. So you could either you do an MCMC or you do multi-nest or whatever. You have to explore your likelihood space. And this, in general, is a very high dimensional space. So there are at least your cosmological parameters. There are many systematic parameters. And there might be other theory parameters if you're looking at, say, galaxy data. Now, at each point in your parameter space, you have to find the value of the likelihood. So irrespective of what the form of the likelihood is, you need the theory prediction at that point of your space. Okay. Typically, in an analysis, you would make many thousands, if not millions of calls. So you need some way of generating the value of the likelihood extremely quickly over this entire parameter space. Now, the problem is that there is no closed analytic form at the level of the accuracy needed. You can make some ambiguous arguments and get answers to 10%, and you can get a closed form expression. But given the quality of the data, this is no longer sufficient. Now, it so happens that if you're in the linear regime of the fluctuations, you can use some Boltzmann codes or something which are fast enough that you can actually evaluate the likelihood on the fly. So every point of likelihood space that you visit, you can actually call the Boltzmann code. It will give you the answer in a very quick time, and you can do this on the fly. If you're in the beyond linear but still perturbative regime, you can still do some similar optimization methods. So these plots are basically plots from these Boltzmann codes. What happens to the CMB power spectrum as you change, let's say, the number of neutrinos in the universe or the total matter in the universe and so on. These calls are very, very quick, sub-second, so you can do this on the fly. And these methods cover most CMB analysis as well as large-scale structure analysis, which restrict themselves to large scale. So you're either in the linear regime or in the perturbative regime. But the next frontier of cosmology, or in large-scale structure, is to harness the information from smaller but nonlinear scale. So here, gravity is driving the perturbations into the nonlinear regime. There's a lot of information on those scales, and therefore could provide much tighter constraints on your model. So it's definitely worth going there, but it presents challenges. So what are the challenges? First of all, you can no longer perform your theory calculations with pen and paper. you absolutely need numerical techniques. There are additional complications related to galaxy formation physics. So, if you have a survey and you see a bunch of red galaxies, you don't know how they relate exactly to your underlying theory model, which is typically for dark matter, but let's not get into that. So it is challenging, but it has a number of expected payouts. So how do we generate theoretical predictions for the nonlinear scales? So what we do is we use what are called n-body numerical simulations to evolve the dark matter field. So I'll show you what this looks like. So you'll see that at the start of the movie, the points are distributed pretty uniformly throughout the space. So that goes back to the initial conditions where the universe is close to being homogeneous. The fluctuations are very small. But as time evolves, gravity drives the formation of these nonlinear structures. So you can see some very high density environments. These are the places where the galaxies will finally end up living in. You see these filamentary structures as well as completely empty voids and so on. Okay? So this is telling me the state of dark matter at the redshift that I want. But these are extremely numerically expensive. So running a simulation at the resolutions that we need will take order days on order thousands of cores to run one simulation. Okay? Additionally, this simulation will just tell me about the dark matter. But what we see in the survey is where the galaxies are. So we need additional recipes for connecting galaxies to the dark matter halos or virialized structures that we see. So these will be the virialized structures, these high density environments. Okay? Even that step of connecting dark matter halos to galaxies, while they have a lower computational cost, they are still quite expensive. So therefore, generating theoretical predictions at arbitrary locations in parameter space is almost impossible to do on the fly. Okay? So we need to come up with some other strategies. And this is where emulators come in. So what we are basically doing is we are figuring out ways to do interpolation in high dimensions. Okay? And this is done using machine learning techniques. These also go by the name of surrogate models. But in cosmology, for some reason, people like the term emulator. So we'll stick with that. There are actually a bunch of groups across the world now who do this. I think the first group was the Cosmic Emu group out of Argonne. But now there are others. I'm part of the Emulous group. So I'll show you some results from the Emulous group. But just bear in mind that each of these groups have equivalent results and analyses. Okay? So how do we build this emulator, okay, which will allow us to do this high-dimensional interpolation? It begins with designing your simulations. So you have to ask the question, if I want to optimally interpolate in these higher dimensions, where should I run my simulations? I have a finite computing capability. I can only run, say, 30 simulations. Where should I run these in parameter space? So you could start by thinking that, okay, let me randomly sample the space, but that is suboptimal. The most widely used technique is what is called the Latin hypercube. So if you have, say, 40 simulations, you divide each of your parameter directions into 40 equally spaced bins. And you pick only once from each bin in each dimension. Okay? So if you did a random sampling, you would end up with something like this, where you might have two simulations at the same value of a particular parameter. But if you do the Latin hypercube sampling, if you look at each parameter, each value is sampled once. Okay? So that is Latin hypercube. The unoptimized Latin hypercube might end up looking something like this, where the points are somewhat clustered. So you might have to do some more optimization to break up these clustered points and give you a more uniform sampling like this. But those are the details. So these are the places in parameter space where you run your training simulations. You also have to run some test simulations, which will allow you to test the accuracy of these emulators that you're building. Okay. And just to mention, there are other techniques which include snowball sequence and so on to determine the design of these simulations. Okay. Once you have these simulations, now you have to somehow build your emulator. So you run these simulations, you measure whatever observable you want, the 2-point correlation function. So you have the 2-point correlation function measured at each point in your cosmology space and your galaxy formation space. And now you want to build your emulator. A lot of the current emulators in cosmology actually use Gaussian processes. There are some which use something called polynomial chaos expansion. But the idea of Gaussian processes is very simple. It is the generalization of a very simple idea of bivariate normal distribution. So if you have a bivariate normal distribution in x and y, and you get a value of y1 for your draw of y, then the conditional distribution of x is still a Gaussian with a shifted mean and a modified grid. Okay? So you see these expressions up here, so you get a shifted mean, even though the original mean was 0, let's say. And your width is also modified. You simply promote these ideas to higher dimensions. And so instead of sigma x, sigma y, and sigma xy, you get matrices. So what you're really doing is you're considering that the input training data, so this vector y, at locations in parameter space labeled by vectors x, have a joint multivariate distribution with the test data, let's say y star, at location x star. Okay? So then, using the idea of multivariate normal distributions, you get a very specific prediction for the mean value of y star at x star and the spread in y star at x star. Okay? So all of this is actually analytic. You don't need anything fancy here. Now comes the crucial part. You don't know what this covariance matrix is. There is no physical principle which tells you what this covariance matrix is. But if you know the covariance matrix, the interpolation is very simple. So the whole game is about learning this covariance matrix from the simulations that you ran. So to do this, you assume some form of the covariance matrix. Widely used form is this double exponential, which says that if 2 points are very close in parameter space, they are more likely to be correlated with this functional form than if they are farther apart. So you introduce some hyperparameters, these L1s, which control how quickly your predictions change along each direction of parameter space. There's some overall amplitude which controls this. And then you try to select the hyperparameters by maximizing the log likelihood of the training data. Okay? All of this is publicly available in codes like George. There are other implementations as well. So this is a very well set up problem. And this training process takes up actually much less time compared to running the simulations and post-processing to get the observables. Okay. Once you build these emulators, it is very crucial to test the accuracy of what you have built. Now for Gaussian processes, I actually showed you that you automatically get an expression for the spread in y star. But it turns out that is often optimistic. So you have to come up with other ways of estimating the accuracy of your emulator. So what do? You have all the test simulations, right? Where you have actually run the simulation, you have actually calculated the observable. So you use your emulator to predict what you should get at the test cosmologies. Okay. So here's a plot showing the accuracy of the emulator over all the test cosmologies, and you can see that this emulator was built to mimic the 2-point function in redshift space, but you can achieve almost percent level accuracy over a certain range of scales. Okay? There's another way of testing the accuracy of your emulator. This is called the leave one out test. So suppose you originally ran 40 training simulations. Okay? You train your emulator using only 39 of them and test for what is happening at the 40th point. Okay? So this is something that you have to come up with. How do you test the accuracy of your emulator? The next thing you can do is you can try recovery tests. Okay? So you put in a new simulation, you put in data from a new simulation with unknown cosmological parameters and unknown galaxy formation parameters, and try to see if your emulator can tell you exactly what the cosmology and the galaxy formation parameters are. So here's an example of such a test. The dotted lines tells you where the truth was, and the red and the blue contours give you the recovered values. So you can see in this case, the emulator is able to recover the values with pretty good accuracy. And finally, you can apply this to data. This has actually been done. This whole emulator framework has been applied to cosmological data. So Jai et al. Applied the emulator framework to BOSS data and constrained the cosmological parameters. So here you're seeing a plot where this is the emulator framework applied to real data. I'll not get into details of what the contours are, but we find that we are not consistent with climate. Okay? So then what went wrong? We have to figure that out. Or is there new physics? Since I'm running out of time, I'll just quickly go through this. You can also build emulators for other observables. So I spoke to you about the 2-point function. There are other observables in cosmology. You can build an emulator for the halo mass function, which tells you the number density of halos at a given mass. You can build emulator for other clustering statistics, such as something called the Mach correlation function, and so on. That actually brings us to the last thing I wanted to touch on, which is building emulators for the field level. So I told you that most traditional analysis in cosmology first brought the field down to the level of summary statistics, and then we tried to emulate summary statistics. But instead of building emulators for every single summary statistic, if we had an emulator for the field, we could then later on compute whatever summary statistic we want. So that is what people are trying out right now. However, this is of course much more complicated. You're trying to predict a 3D field with many features. So you need much more complicated architectures, but this is showing promise. So here is one from Jamieson et al. 2023. There's a paper out on arXiv today, I think, which uses diffusion models to do something similar. People have used GANs to do something similar. So this is an exciting and evolving field. I just wanted to point that out. And so, as I'm running out of time, there's my summary. So cosmology analysis requires fast evaluation of summary statistics in high-dimensional parameter space. In the nonlinear regime, this cannot be done on the fly due to heavy computational requirements of the simulations. Emulators or surrogate models are now commonly used in cosmology, and full analysis have also been performed using these methods, and they've all been done in recent years. There are many open questions about how to design emulator, the simulation design, training choices, and so on, which need to be sorted out. And going forward, people are looking at these full field emulators, which involve deep learning in all its various forms. So this is an evolving field, so stay tuned. Thank you.
I have one question. So it's from a slide. Can you go back to the slides where you were showing the graphs and no, yeah, that one. No, next. Here, yeah. I remember you mentioned the use of multivariate normal distribution, and we know that it is a symmetric distribution, but here it is the presence of skewness is clear. So could you think about
the posterior?
Well, the posterior distribution is something which is not multivariate normal, but coming from a family of that normal distribution, right?
Sorry, this is nothing to do with the emulator. This is actually the posterior for the parameters.
So
where we have no such assumptions of multivariate.
Okay. So it is non-parametric approach.
emulator is used to get the prediction.
Emulator, okay. Even the form of the likelihood I'm not specifying. The emulator is purely to get your theoretical prediction at each point in parameter space. Okay. The likelihood function you can create to be non-Gaussian, etc. That's the emulator process is not really talking about that.
Okay.
Okay, one more.
That's right. Why does the thing diverge both the ends?
Because you're using one particular simulation. This side comes from sample variance. So you are simulating only one particular realization at a cosmology. So the modes you have no control over. So if you simulate twice at the same cosmology but with different realizations, you will have some sort of spread here. Here what happens is shock noise becomes important. Okay, so it's basically noise at the two different ends, which leads to a less than optimal performance of your calculator.
Okay, so let's thank our coach. Let's meet at 11.
11:45. What time?
50. Yeah, please give me the.
Usually not. They're determined in different ways. Like their impact is different on the. But I think we're to cheat all the.
Did you share?
I would remember where they lived.
You want to? Yeah. So,
Different ways.
this one, right? I'm going to enable the. Okay. Just going to create a tiny URL so that it's easy to. So let's start with. Yeah, so that's what we are hoping. Many of these it's yeah. Otherwise, that whole thing copying it. Yeah. Let me open up this so that
I think this is.
take off the screen. Slideshow. Showing the first image.
My presentation.
So, nothing from Aditya. You should put the image from Aditya. If you can get these students. Okay, good. So this one. Who is going first? You are second. You are the right. You are going second. Okay. Okay.
हाँ वही वही इसलिए हाँ इसलिए चलो हाँ हाँ
क्या है करके, हाँ। But three times. कॉलेज वाले अलग अलग कॉलेज स्टैंडिंग
हाँ मैं मतलब हाँ मतलब मुझे लास्ट का टॉप समझ नहीं आया और समझ नहीं आया पहले का ठीक टाइमर्स हो गया ये जब मैंने चीज देखा ना लाइक मतलब वो ग्रेविटी वो जब फर्स्ट
Yeah, we're working with Joe and Sean.
Really long time. Yeah, I know. I'm sort of you are from where? Who was his roommate? He said it's shared or I see you already in the high position. I think you're but I would have come further. Usual answer is very strong inside how you can do that. Okay, so let's get started with the next session.
We do find targets. You can't just blindly type, point in the direction. Distributing does a full image itself.
So, like, what kind of metadata?
Where we are just expecting you to think about to understand the data.
Yeah.
AI can be used.
Hello everyone. So I'm Anil, and today I'll be discussing on talking about IUCAA deep learning. Okay, so basic introduction to an exoplanet. So this slide is basically to show that
the discovery of exoplanets essentially boosted interest in the, look for extraterrestrial life and the field of planetary habitability, and the holy grail in exoplanet research is really about searching for Earth-like planets in the Goldilocks zone of stars. Okay. So the method that I work on is the radial velocity method. So it's basically the planet and the star orbiting around the barycenter, their own barycenter. It creates the presence of the planet creates a wobble in the star's spectrum, and the semi-amplitude for such a signal is given by this formula, which basically we can see that the amplitude for the Earth Sun system is 9 centimeters per second. That was so why are we using machine learning essentially in this? The reason is we want to detect Earth-like planets around sun-like stars. So the current high-resolution spectrographs have precisions well below meter per second. Okay. But the primary signals are actually not extracted very well below a meter per second, and the reason is stellar jitter. Okay, so you can see in this plot that as time passed and the spectrograph qualities, the instrument quality has increased, the threshold for detection went down until it hit block, and this was because of stellar jitter, which means that the convection at the surface of the star was actually creating shifts in the spectral lines which we depend on for the radial velocity measurements, and thus the radial velocities, the actual Doppler shifts because of the spectra, because of the planet was not able to be detected or to be inferred properly. So the mitigation of such effects actually involved selecting certain spectral lines which were not that affected because of activity or the stellar jitter, and this actually led to limited usage of the information that was available for analysis. So machine learning can actually circumvent that. We can potentially use all the information that's available to us. So that is one of the reasons. So the data that we are using is the new spectrograph data, and it's an initial spectrograph that takes the solar observations. So we have detailed solar spectra, and we are basically removing all the signal out from the planets of the solar system and injecting our own planets, our own synthetic planets. So this is a pipeline for essentially creating a representation of the spectrum. So if you use the entire spectrum, it's essentially around 180,000 pixels. Okay, so not all of it is spectral lines, firstly, and secondly, it's too hard for the GPU to process such a huge amount of data for machine learning purposes. It's too large. So we essentially create a smaller version, smaller representation of this using something called CCR, which is a cross correlation function. It's a method to average out spectral lines, and this 180,000 huge data set is converted to somewhere around 1,000 to 1,200 pixels, and that helps in the machine in processing the data. After that, what we are doing is essentially, so what we have in one CCR vector is essentially a representation of the solar spectrum at a particular instance in time, with all the signal from the host planet from the solar system planets removed. It's a static circuit. Okay, we select 100 of these vectors randomly and stack them to create an image. And what we want to do is we want to essentially mimic what could be observations of an exoplanet at random times. So we assign row-wise times to these particular spectra, and inject a Keplerian signal at those particular observations. Okay, and then those particular observation times. So we're mimicking the snapshots of that particular star exoplanet system that we want to simulate. So it's not exactly a simulation because the noise samples are actually here. Okay, it's just the signal that we are inserting to a planet, which is actually synthetic. So this is what that image looks like. You have 100 different spectra over here, and if you subtract the first row, because it's essentially the same data, then you get a smaller representation of the same data. So what are we doing here? So this was data selection and processing, by which we converted this spectrum, which was looking like this, the raw spectrum, into something that looks like synthetic data. So the synthetic data means that the planetary signal is synthetic, the noise samples are real, and they have been shuffled to prevent any time correlation. And we have a deep learning model architecture, which is used to train on this synthetic data. Then we get a trained machine learning model. And of course, there is a separate validation data set, which the trained machine learning model can be validated, the predictions can be verified. So what are we doing here essentially? So what predictions are we doing? So the Keplerian signal that we are inserting, okay, it has certain parameters, the orbital period of the planet, the semi-amplitude of the planet. And what we are doing is we are sampling in the period and the amplitude. So P is period and K is the semi-amplitude. So the period is sampled from a log uniform distribution. So the planet can have a period of 12 to 65 days. And log uniform means that it's uniform, log P is uniform. And similarly, amplitude, semi-amplitude is sampled from values of 0.05 to 3 meter per second. All right, and these are mapped to 10 uniform bins, which are labeled 0 to 9. Okay, so for example, 0.05 to 0.345 will be labeled 0 for K, 0.345 to 0.64 will be labeled 1, so on and so forth. And the output is a probability array, which basically will have an array of length 10, and each element of that array will tell you what is the probability of that particular parameter for that particular signal, lying in that value range. So it essentially is converted to a classification problem. So if you have a binary classification for cats and dogs, then this is a 10-min classification of parameters for the periods and the amplitudes. This is essentially a schematic telling you how the deep learning is working around. So you have an image which is passed to the neural network. It prints out the probability array, and the maximum value of that probability tells you, well, what is the predicted bin label, what is the predicted range of that particular parameter. It's compared to the actual bin label, which is taken from the actual input parameter which we have, and then we compare those two mapped and predicted labels, and loss optimization and backpropagation eventually, updates the weights of the neural network, and that's how we train the model. Okay, so the first model that we tried out was convolutional neural networks. Okay, so they are standard machine learning model for image classification. Okay, so what we are trying to do is basically separate the signal from the noise over here. So we use the input layer essentially had the image with the signal inside it, and we use convolution 4 times to essentially get out a probability array which predicted the particular parameters that we wanted. And which were period and accuracy, and the accuracy was around 69% for period and 43% for the amplitudes, which was not really great. Okay, because the random accuracy is around 10% because you have 10 different bins. So we moved on to another model, which was the long short-term memory. So it's a useful machine learning architecture for time series problems. And we had uniformly spaced timestamps for this. And again, there was a softmax layer for prediction of those 2 parameters, and essentially it improved the prediction of these 2 parameters. But there was a big problem with these 2 models, is that neither of these models actually worked when aperiodic timestamps were used. Because astrophysics, you never get observations which are equally spaced in time. You will have to work around with it. So this was a problem. To solve this issue with aperiodic timestamps, we turned to widget transforms. It's really a state-of-the-art technique, very recent. And if you have heard Astronomy talk, then you know that transformers essentially deal with correlating 2 different patches of the 2 different sections of the text, and used to translate it into another language. Let's say those are the LLMs. But what we're doing is vision transformer does the same thing, but it does it for images. Okay, so it divides the image into patches, and each patch can be, you can think of it analogously as a word in the transformer model, and it also deals it in the same way. So you have embeddings, you have positional encodings to tell where in image the particular patch is lying, the particular pixel is lying. And again, you have this self-attention mechanism, which deals with having a correlation between the different patches and different pixels of the image. And you have standard encoded model, which connects to the multi-layer perceptron and gives out the probability of these parameters that we are trying to analyze. Again, there are a number of heads here, which allows us to parallelly compute all these, which increases the speed of the training and helps us train faster. So for the attention mechanism, if you want to know more, you can see this. So you can refer to Aswani's paper in 2017. Attention is all you need, and that'll tell you more about how this entire mechanism works. So the results that we achieved were much more impressive compared to CNNs and LSTMs. We got around 85% accuracy for period classifications, and amplitude classifications we reduced it to around 5 bins instead of 10. So we basically merged 2 adjacent classes into one. So you got 5 bins instead of 10, and we got a great accuracy of 91% for amplitude classification. And in comparison of CNNs and LSTMs, it showed that VITs can actually help us, deal with aperiodic signals and thus improve our results. So this is a sample of high confidence period predictions for. So this is a certain amplitude bin, so 0.64 to 0.95. If you recall, the threshold for radial velocity was around 1 meter per second because of the effects of activity, stellar activity. So we are going one below that, so 0.64 to 0.95. You see that around 73% of data is classified as high confidence, which is like the most probable bin is greater than 90% probability. So you see that the predictions are pretty much a straight line, which is what you expect for a good model. These are the results for different machine learning models. So you have the accuracy variation with you see that the transformer outperforms the irregular timestamps for the transformer outperforms the regular timestamps for both the CNN and the LSTM. And this is a key accuracy variation, which is predicted for the transformer with the 5 bits, which is also quite high. And finally, we have a semantic check. So we had trained this completely on samples which had signal in them. So we verified this with samples with no signal, and we expected it. We tried we predicted the k values for these using the training models, and what we expected was that it should basically predict the lowest possible bin for the amplitude, because if there is a signal, then it will give a higher amplitude. So that is what transpired. So you had 50,000 images with essentially no signal, and you had 2 different models with 10 bins and with 5 bins. And for the 5 bins model, essentially the label was 0 for almost all but 2 images. For the 10 bins, it was somewhere around 100 images, 150 images, which gave other signal, but mostly it was the lowest bin was what was predicted. So you got around 99.72% for the 10 bins model mapped to bin 0, and the conclusion was that it's indeed detecting the Keplerian radial velocity signal, not just some arbitrary RV source. And so, yeah, so conclusion is that the radial velocity model method is characterized of stellar data, and I mean this is the summary. And I'd also like to discuss some future work that we are planning to do. So essentially, we are also dealing with. So there are cases where you are not sure that whether the planet that you have detected is really a planet or is it an effect of periodic stellar activity. Okay, so what we are doing is we are planning to. We are working on right now is creating fake planetary data, which looks like periodic, creating fake activity data. So it simulates a planet, but it's not. And trying to classify if it's really a planet or if it's not. And it turns out that it's in the pipeline, and the results are quite promising. And another project that we're working on is essentially for other stars. We want to use this. We don't want to just limit ourselves to the sun. We want to move on to other G-type stars and eventually other stars. So one thing that we're working on is essentially for other stars we have limited spectra. We don't have a lot of spectra which we can train on. So we want to basically create more spectra for ourselves. So we are dealing with variation order encoders and diffusion models to generate more spectra for other stars. And first we'll do it for Sun, and then we'll move on to other stars. So those are the projects that we are working on currently. And I think that's all I will keep on.
Which platform have you used, like Keras or Python?
Oh, for the first two models, CNN LSTM, we used Keras, and we moved on to PyTorch for the vision data.
Okay. Any other questions? If not, then maybe we can move on to the next speaker. So next, we'll learn about deep learning techniques for solar flare predictions. Yeah, this should work. Yes, I think so. Quantum is this one's a quantum and this.
Yeah, so hi all. So I'm Lim. I'm a research scholar working on various applications of AI to astronomical problems, and this is one such problem that I'm working on. So this was a part of an ISRO and funded project, which has an eventual goal of applying solar flare predictions to data coming from our own suit called Aditya. So the talk is titled Deep Learning for Solar Flare Predictions, and these are the collaborators that I work on. Okay. So the outline of my talk would be starting with why are we doing this and how are we doing this. And then in the later part, I'll be talking a bit about using interpretive techniques related to what Manish talked about in the last talk. So let's start with the motivation. So whenever you see a sunrise or a sunset, it's always a calming thing. You feel like the surface of the sun is very calm and quiet over you. But even if you zoom a bit, you might see some spots on the sun, which we call sunspots, but that's pretty much it if you look at fully in the visible light. What you're seeing here is a photosphere of the sun. But as we know, sunlight is composed of different colors as Newton showed us, and you also know that the sun has a black body spectrum that emits in various wavelengths. So instead of looking at the whole light, the illuminated light, if you just use the separate filters to view the sun, how does it look? So it looks very different, right? So it looks, the sun is actually a very active, sun has a very active atmosphere. It is very dynamic. And as you can see, there are a lot of activity happening here. And if you notice, you can see that there is some violent outburst or much more violent activity happening here. So this is actually a flare, but you can see a better in a different filter, I think. So if you look here, yeah, you can see that this is a flare that happened, and this has actually saturated the CCD and this caused diffraction patterns and everything, just visible in the 94 wavelength band. So yeah, so another aspect of this is like, what are these? What are the places? Is the sun fully active, or are there the activity of the sun is actually limited to certain areas which we call active regions, and the active regions are characterized by their by the complexity of their magnetic field configurations, and we can create things called magnetogram images from the visual observations using, because of the Seaman effect that helps us to measure the magnetic field using light coming from it. So this helps us to create. So this is what I call the magnetogram, which shows you how magnetic field is distributed across the sun surface. You can see the white and the black shows opposite polarities, and the gray, so there is not much magnetic field. So such magnetograms show you where activity in the sun is happening. So it corresponds to the sunspots you can see. There is a relation between that, and you can see wherever there are sunspots, there are a lot of activity happening. So these are the different wavelength bands that we have. So this is all coming from the AIA instrument about the Solar Dynamic Observatory. Okay, so in short, what you just saw is just a flare. So what are flares? Flares are impulsive outbursts of electromagnetic energy that occur on the sun, and flares has an impact on the space weather, and in some cases it has a very disastrous effect that is felt on Earth. So there is a lot of practical value to be able to predict solar flares. So how has this been done previously? Is that there are actually lots of methods. I'm just highlighting a particular work that was done in 2015 that used a traditional ML approach to do the solar flare prediction. So this used something called an SVM, or a support vector machine, and it didn't use the magnetogram data directly, but it derived features. A lot of these features you can see from the magnetogram data and used it for training an SVM. And all these networks have not surpassed the existing benchmarks by a very big margin. So there is actually a lot of scope for further improvement. So this is where the deep learning comes. And the short, but there's something I have in this talk. What I have done is we have shifted the goal of predicting solar flares to a simpler goal, which is to classify an active region. So our goal here is to train a deep learning model that can distinguish an active region that has flared from one that has not flared. So this is an initial part of the work. So in order to do this, what is the data that we have used? So here we could have gone and created our own data set, which I did try, but you can use the JSOC data center, which has the AAA or data, and it also has a special data product called the HMI active region patch, which is a patch of it's an active region patch that is mapped continuously through the life of an active region, which tracks exactly where the active region is on the sun's disk, and we have all the data for such patches. So that is all available to you. But so to quickly get into this work, we used a particular data set provided by these authors. It's called an active region, AA active region patches, or ARCs in short. This is actually subsampling in both spatial and temporal dimensions. So it is taking cutouts of the arcs, and so that's how it's spatially downsampling it. And the temporal downsampling, it's only observing in some particular time windows, with gaps in between. So this is meant to bring down the huge data set size. But this is what the data that we are just working with. So you can see an active region patch, how it looks. The one that is actually obtained from this particular data set. You can see this kind of activity happening. So how do we label this active region patches? So this is now a binary classification problem in which active regions become our inputs. But the two classes are one active regions that have flared and one that are not flared. So how do we know if an active region has flared or not? If by using the X-ray plus data from the GOES instrument that continuously monitors the integrated X-ray coming from the solar disk, and based on that we can know whether the flare has happened, or if a flare has happened, it also tells you what the power of that X-ray, the power of that flare was. So that is comes under these labels. X class being the most active flares, and the one which I actually showed in the video. So this is like a representation of a model. So we are using an AlexNet, which is a convolutional neural network, CNN, and we are using about 7 or 8 input channels. That becomes an input. This comes from the various AA bands, and we run it through the CNN, and we get it's not exactly forecasting, but a classification result from the presentation of our network. So these are the snapshots, those are images. These are the active region patches. These are images. Yeah. Yeah, so there is also a particular challenge here that active intent patches can be arbitrarily sized. The shape can be anything, but usually CNNs expect the data to be of a fixed size. So we have to somehow pad it or crop it. So that creates its own problems. I'm not talking about that now. So these are the libraries and framework that we have used. We have used TensorFlow and Keras currently. And this is just a LandDB, which is an interface for better visualization and logging of your various training events. Okay, so that is pretty much what I was talking about when describing what we have done. So I come to the results when I show you the interpretable AI part, because the interpretable AI, the goal here is to why interpretable AI is important is that it is also a way to understand more about the data that is fed into the input. So this there are obviously gaps in our understanding of what causes or what triggers these flares and everything. So we probably don't understand the data that we are giving, but by training a model to do some classification tasks and then trying to interpret it is a way of understanding more features or more about the data that we have. And it also definitely helps us understand and debug the model. So when you are developing the model, so instead of just looking at graphs of loss we are decreasing or confusion matrices and things like that, it is always helpful to do some interpretability to be able to understand what the model is picking up on and to be able to debug the model. So this is the idea of a particular form of interpretable AI called integrated gradients. I think Ashish mentioned it. So this I have shown linked a tutorial from TensorFlow on documentation. This is actually very good and which I used from which I've taken some of the pictures here. So this is an ImageNet classification, I think, which has random classes. One of it is the Firebolt and one is a giant panda. So the goal here is to be able to create saliency maps as shown here, where this is like a heat map or something which shows highlights what in the picture has the model picked on when predicting it properly. So a well-trained model, when you try to reverse engineer or when you try to interpret it, you want to know what features or what pixels exactly are responsible for these predictions happening. So this is also called as a pixel attribution method. So this is how it looks for the panda. This is a baseline I will talk about. This is a black image. And this is the mask created with the importance score. And this is the this mask overlaid on top of this with a particular transparency. So the earliest way of using interpreting a model was by just using gradients itself. But the gradient, as you may know, is directly showing how much a particular pixel is contributing, or how much the probability of a network changes with respect to particular pixels. So it could be used, but the one problem with that is that it has a saturation that happens. So just directly using gradients are not that useful. So that is why we use integrated gradients. And the procedure here is to start with or establish a baseline image. So where sometimes you can think of a baseline image as being a pure black image, or a pixel as being particularly fully black pixel. And you take any other pixel in your image and you use this pixel, this black pixel, to show that the absence of a pixel or a feature. So you need a baseline for it. If the pixel was particularly absent, what is the performance? And so you need to set a baseline. And it is for this reason that we, in order to establish a baseline, we use that black image in the beginning. So we use a black image, and and the next thing we do is to interpolate images. So that is, we start from a pure black image, and then this is our actual image, and we create interpolated images along the as an alpha value from 0 to 1. You can think of it like a transparency. So you vary and you create different interpolated images. So if we focus on one particular pixel of this image, if we focus on one particular pixel here, you are actually taking a baseline and interpolating that pixel from that 0 value to that. You are trying to find all those with a particular interval, obviously. And then you're trying to predict on all these pixels and trying to see how that variation happens. So we establish a baseline, we interpolate the images, and we predict on the interpolated images, and we compute gradients, and we accumulate the gradients over the interpolated images. So we are actually adding together all of the, if we take a particular pixel and we do the variation in the alpha, and we add together all of those values to get a single score for a pixel. So this is the idea of the integrated gradient thing, and this is the formula for that. This is xi is a particular input, and xi dash shows your baseline, and you take the difference, and this is where you interpolate. This is showing you the interpolation. Yeah, and then this is clear that you create your interpolated gradients, interpolated images, and you take the dou f. So f here is your model's prediction function, and dou f by dou xi is the vector of partial derivatives of your model's prediction function related to each feature xi. Feature here in this is obviously your pixel. So with respect to each pixel, how much your model's predictions are varying. So that becomes this gradient that is computed, and that is averaged over and multiplied with the difference. These are like the equations involved. It's very quite simple. This is what I was mentioning. So using all of this, so this was something that I was just trying some days back. So I was trying to do this using the tutorial that was shown, and I'll show some of the results that we got. So this is how our model training happened, and once our model was trained, it's continuously being developed, but on a particular version, we tried doing this kind of analysis, and I didn't get time to make it that better, but I hope you can see that this is an active region that is on the limb of the sun, and there are these loops that are there, and you can see that it has detected some pixels along this and given them some attribution and given some scores, and you can see them, I think, in these overlay images. So this is another, I don't know how good this came out to be, but so there are some pixels here that are picked up. It's not that good. So this is the same thing that visualization of the gradient saturation happening using our trained model. Okay, so so this was what I had, and if you're interested in more reading on interpretable AI, this is a book I came across, and this is a very good article on Distil that talks about how different baselines can have its different effects on your attribution.
Questions for it?
In your CNN, have you tried combining all the images into a 3D thing and using that or movie?
Yeah, I had that question to ask to him also. So regarding, so this is currently like a single image with no temporal thing. But I want to know how we could use something like a vision transformer or something that can catch this dynamics happening. That we're thinking about that, but currently I have also used a 3D CNN in another additional work that I have done. So that is some radio galaxy classification. So I was thinking maybe something like that, which considers the time evolution of the active region rather than separate images. We're not.
Any other questions? If not, let's move on to the next talk.
Hi.
So next we'll hear about advances in stellar physics.
Hi. Okay, thank you very much for having me. So let me begin. I'll just jump straight in, and then I want to take a minute or two to explain the sociology of this machine learning and what we're doing and so on. So, okay, my title was very brief. I apologize. I should have come up with a better title. This not great, but it just says astroseismology, but we made really, really exciting advances on the topic. Okay, so what is astroseismology? So seismology is the study of objects whose surfaces you can see through their oscillations, right? So for instance, the Earth oscillates, and then you can measure its free oscillation spectrum at the surface. The Sun oscillates, all the balls of gas in the universe oscillate. And for some selection stars, if they're sufficiently bright, you can measure their oscillations at the surface. And with the Sun, of course, you resolve the disk, and you can go to very high degrees and you have spatial resolution and so on. But for distant stars, you have individual pixels of light, so you can only get a time series. But the Sun, of course, you observe one star with high resolution, so you can really get very detailed images of what's going on. But for distant stars, you get thousands or hundreds of thousands of them, but small amounts of information. So you can test different theories based on these types of data. And so we've been able to use now these oscillations for the better part of decades now to infer differential rotation, which is that every latitude and radius, so let me rephrase that. Rotation is a function of both latitude and radius, we find in stars. You can see that in Jupiter, for instance, you see that different latitude bands rotate. It's called superrotation when we discuss planets, but when we discuss stars, it's called differential rotation. It's a very complex angular momentum processes happening there. You can measure magnetic fields. Actually, it's really remarkable that you can say all of these things about stars. And then ultimately, we want to test the theory of stellar evolution and challenge it and potentially improve it, and so on. So that is the grand program. Okay, so now that being said, I just want to take a minute to say a little bit. So we've been transitioning slowly away from conventional 20th century methods to machine learning. This is not to say that somehow this machine learning is some black box and we just throw our hands up in the air and throw some data at it and hope for the best. That's really not the case at all. But when my students have given talks, I find that there is there's some wild and complicated emotions from very distinguished physicists. There's either a sense of some sense of despair and hopelessness and the deep suspicion about the result, or there's some wild enthusiasm that it can detect anything. Machine learning can detect all manner of patterns and tell you. So neither of these is true. Unfortunately, both of these I find have left the field in our field, and I'm sure this applies to other areas in astrophysics. It's a certain degree of helplessness of the physicists. So people are launching instruments that are billions of dollars. Kepler was $1 billion, TESS was $1 billion, Plato was more than €1 billion. All of these are billion-dollar instruments that are being launched, which will eventually look at hundreds of thousands of millions of stars. But our methods have been literally invented a century ago, but have not improved, not a century, but less than a century ago. MCMC, which is the gold standard, is, for want of a better word, excruciating. So it requires a very highly trained human being, of which there are very few on this particular topic, to sit and spend hours and hours and hundreds of thousands of CPU hours with a finite chance of success. So for instance, you measure, let's say, a spectrum. I'll explain this in a minute. And you want to fit the spectrum to get the parameters of the star. That's the goal. So then you use an MCMC, and you could literally spend a month doing it, and it could fail. And there is no alternative, really. And the community has not moved at all to try to fix this. They're moving by the glacial pace, not faster. In fact, all the instrumentation, the launches are moving much faster than the theoretical progress, which is, in my opinion, quite stunted. So this is what my group, and we have seen a great opportunity for in India. If you're abroad, and we'll stop with the sociology and discuss my results, but if you're abroad, it's very difficult to suddenly switch and say, I'm going to apply machine learning to science, because you need funding. You only get funding if you're already done something, but how would you do something if you don't have funding? So, it's like a chicken and egg problem. And so they've just moved glacially slowly. But, in India, you don't have that problem. You have students who are actually extraordinarily good, and then you can really make rapid progress without a problem. So that's what we proceeded to do. And so now my group almost exclusively does this. So all of these are papers. We've been crouching for years. We've been crouching, tuning, testing, So ever since, I would say 2019, we've had these results. So 4 years we've been testing and making sure all of these results are correct. So I'll show you all the results. There is very little talk about machine learning. There is only slides about the results that we have. So this is a summary of the things that we're doing. It is not an exhaustive summary, but it is a summary. So I'll discuss this stuff. But one of the most exciting things to me right now is galactic archaeology, is to use hundreds of millions of observations of Gaia to try to age stars, main sequence stars in the galaxy and red giants and so on, which we think we're very close to doing now. So this would be really a profound result if achieved. So we're doing a lot of other stuff. This you heard from my student, who's okay. So let me just go into the results and explain to you what this is. A red giant. Okay, red giants are complex oscillators. Now this number is 2, 0, 2, 0, and 1 represent. As I said, you can't resolve the disk of the star, so you can only get the largest scale oscillations of the star. So in this case, this is L equal to 2, which is a spherical harmonic degree 2, 0, 2, 0, 2, 0, and these are labels for the star modes, right? This is a spectrum. On the horizontal axis is temporal frequency, vertical axis is amplitude. So we take a long time series, we do a Fourier transform modulus squared. Okay, that's exactly what this is. You see a forest of peaks here, but if you look carefully, you see 2 and 0 are approximately equally spaced here. So these are harmonics that are fundamental in higher harmonics that are equally spaced, but then this stuff is very complex here, right? And so I won't describe any more physics, except that hidden in all of this stuff are all of these parameters, okay? So this, if you are able to correctly fit, in this case, we have fit the data with a simulation, MCMC in this case. By fitting this, the fit is extraordinary in this case. You can get all of these parameters, the rotation of the core, rotation of the envelope, and it will test the most profound things in stellar evolution just from this 1D time series, which in itself, I think, is a remarkable feat of physics, right? So you can detect all of these things for at least some class of stars. Okay, so we want to get the size of the star. We want to understand how that's changing as the star evolves. We want to know what the core, ignore this parameter for now, it doesn't really matter, but we want to know how angular momentum is being transported in the star as it ages. We want to understand what magnetic field is doing in the star as it ages and so on. Okay, so what we do after, this was the back-breaking work, so basically what we do is devise high-quality synthetics. Day in, day out, the bread and butter is to develop it's because we only have a finite number of labeled observations, or high-quality labeled observations, a very small number, hundreds, perhaps 1,000, right? So what we do is we use the theory, in this case of the asymptotic theory of stellar oscillations, and we build millions of spectra. But these spectra at first blush and look nothing like the observations. So we tune and tune and tune and tune. This stuff took 2 years to do, to basically get the spectra to look as close to the observations as is needed, right? And then we have an unlimited number of observations, or other synthetics, right? Then we train the machine. This is in CNN and STM, and simultaneously we get the entire PDF. Okay, so we're not outputting the entire PDF. So all of these parameters, here, but we are basically getting the marginal PDFs for each of these. Okay, so this dashed line for this particular star is the MCMC result, and this is the PDF that we get. So what we've done is we've converted this regression problem into a classification problem. Each bin, this is the bin problem, each bin is assigned a number, a probability. So that's how we get a PDF. We get double peak PDFs, triple peak PDFs, all of this stuff. We compare the PDFs that we get to MCMC PDFs, and they're basically the same, except of course the sampling here is coarser than MCMC. MCMC is very finely resolved. So we're doing as well as the MC. In fact, I think we're doing better than MCMC for a variety of reasons that I'm happy to get into if we want to discuss later. So each of these parameters is correctly inferred. This is core rotation, you can't see it here. This is envelope rotation. So we expect, okay, now that's it. This is the thing now, I'm going to go into the results. But we expect that as the star evolves, the core contracts, the envelope expands, and the envelope slows down. It becomes slower and slower because this thing is becoming giant. It's a red giant, right? It's huge. The radius is huge. Angular momentum goes as r squared, so the outer envelope is slow, very, very slow. Even the core spins down with time. That's what we expect. This is the general understanding of this. Okay, so the first result, which is the least impressive of the results, but already a significant contribution, is the estimation of this Q. Okay, so this plot is what I want to draw your attention to. These are the published values that were published several years ago. And you can see they seem to flatline at about 0.1. Now, there are two reasons why this is the case. Okay, the two reasons why this is the case is that one, it is very difficult for the MCMC to converge when Q becomes smaller than 0.1. So sometimes in some of these people's codes, they hard code it. They say this is the lower limit. Okay, so they can't actually even go below this. The second issue is the spectrum itself contains all of these this amplitude information. That amplitude information is ignored in some of these current evaluations, and so they don't know how to estimate these low values of Q. Whereas in our case, when we do the analysis, we take uniform distributions of delta mu. We do not prejudice our result in any way. Uniform distributions of delta mu, delta pi, Q goes from 0.6, over some, basically a full range of each of these, right? So there is no prejudice, there's no intrinsic bias in the values of Q. So we're training a machine over a full range of parameter space. And so it turns out that MESA, which is the industry standard for stellar evolution calculations, was predicting this, that the Q in fact should fall with this delta mu, right? And but so far in the published literature, this is what people were showing. So anyway, so now we're able to show that these two match quite well. Okay, so this is one of the results that we had. Then the next result is for rotation, which I think is one of the nicer results that we have. So here are the rotation rates of the envelope, of the core, as a function, as a function of delta mu. Okay, so delta mu is the envelope is roughly connected to the size of the envelope. So these are stars that have just exited from the main sequence into the subgiant phase into the red giant phase. These stars are the youngest of and as delta mu decreases, these stars are getting older and older and older. So these are the oldest stars that we have at delta mu of 4 microhertz. And so what you expect is exactly what's happening here, right? So things are falling, and this is what you expect. What you do not expect is this type of stuff here. So there is a class of stars here that is rotating between 10 and 100 times faster than they ought to, right? And so that is extremely surprising. So now we're working with Ethereum, so we've worked with Ethereum, this is currently with you, where we try to explain these anomalous stars. And with an MCMC class method, unless you looked at each of these stars and fit each of these stars, you would not automatically detect these, right? So you would have to, it would take too long. You wouldn't know which stars to look at. So this is an excellent anomaly detector. So the machine learning has detected all these anomalous stars here. We expect some fraction of these to be anomalous, but we don't know which ones they are, right? Till we run this. And so for many of these, we've confirmed with MCMC that they are the correct values. So this is why it's taken us so long to get these estimates and to build reliable understanding of these. So this is envelope to core rotation for this sample of stars. This is all from Kepler. These are all Kepler observations. And again, as I said, what you expect is the envelope will slow down dramatically. This horizontal axis is solar radius. Okay, so as the radius expands, you expect that the envelope will basically almost stop rotating in comparison to the core. So this number should basically keep falling, right? But that does not seem to be happening at all. So you can see that you see some class of stars. In fact, the envelope is rotating faster than the core. This is a very unexpected result because the amount of angular momentum that the envelope will need to have is substantially more than it's theoretically allowed. So this is forced. So we're working with Jim Fuller, some of you may know him, who is helping us interpret or theoretically model this. And we think these are merger events. This could be the stars swallowed a planet, or stars swallowed another star, or something like this. But this is a highly anomalous class of stars. We've tested a lot of these with MCMC, so we know that definitively that there is at least a few of these stars are true in the sense that the envelope is rotating faster than the core. So this work is currently under review. Okay, so that's about rotational dynamics, right? So then there's this diagram called the delta mu delta pi diagram. So you can see what the meaning of these parameters are here. So what's been known for nearly a decade is this line. So most of these R represent red giants. R says red giant. C says clump. Clump is a late stage red giant basically. And so this has been known for up to a decade now. This relationship between delta mu delta pi. What has not been known is this. There's a new and suddenly unexpected relationship here. So So this evolutionary pathway, so that it goes from a main sequence, exits into a subgiant, and then subgiant to red giant, and you expect that it goes down eventually through this line, this particular relationship. And what this is quantifying is that the core is contracting and the envelope is expanding at a certain rate. This is what this is suggesting. But this is actually suggesting that there are two different, there's another preferred rate. It's quantized as well. You don't see a continuous distribution from here to here, but there's this or there's this. This is entirely unexpected. So we've been working now again with the MESA models to try to understand why you have this quantized rate, why you have this different evolutionary pathway here. Again, not known to the community because they just expect that everything should follow this standard evolutionary pathway. Okay, so that's one result on structure, which we've not yet submitted, but it's going to be submitted soon. So now I spoke with a colleague of mine, some of you may know him, Lars Filston, one of the developers of MESA, the later developers of MESA, and he suggested, look, there exists about 2% of these stars, of all the red giants, exhibit a certain helium flash signature. And in general, it has not been observed conclusively before. And he said, look, it should, in this delta nu, delta pi space, it should be around here. And no one had detected it before. And so we did, again, as I said, we did not do anything. So I had a call with him at 9:30. I spoke to my student Siddharth at 10 o'clock and I said, Siddharth, can you look at the data and you see there's a signature of this. And then an hour later, we see that there is in fact a helium flash signature. This is a helium flash signature. And remarkably, you can see all these other interesting properties. Okay, so you see this, as I said, these two quantized things. There's something funny happening here. There seems to be some type of nebulous structure. We don't have enough samples yet. There seems to be some type of nebulous structure here. There's this helium flash signature here. You can see that there's a different clump phase here, exotic clump phase that was not known before. So there's another one here too. So there are multiple evolutionary pathways. Again, if you had to do this, it would take like 50 years. I don't mean to underestimate the current existing number of people who can do it and the amount of computational resources that exist to analyze a still sample of stars. You would have to fit each one of these with MCMC. It would take you forever. And so it's not feasible with what we have. You need these methods to be able to scale it up and look at the entire ensemble in literally a minute, right? That's all it really takes once you train it. But we see multiple evolutionary pathways for which we don't have explanations yet. And but anyway, this is helium flash, and this will hopefully be explained soon. But yeah, so representing all this really remarkable physics that we can get out of this right away. And one thing I want to say about astroseismology is that one instrument. So in a lot of astrophysics, you have to corroborate things with multiple different instruments. So in GWST, you look at something else, then you look at something else. Each one providing a little bit of different types of information on this, right? But with Kepler and with TESS for astroseismology, you can literally only look at this one instrument and you don't have to look at other instruments. So it represents a wealth of information about stellar evolution in that one instrument. Okay, so I will wrap up with this one thing, which in fact I'm most excited about. So delta Scutis are a class of stars. There's lots of different stars. Even stellar physicists don't necessarily know all the classes of stars that exist. But delta Scutis are a class of stars that rotate extremely fast. They rotate so fast that they become oblate, like American footballs. They're not spheres anymore. The sun, for instance, in comparison, is almost a perfect sphere. And so because they're oblate, their oscillation physics, they're rotating. Some of them rotate so fast that they undergo Keplerian breakup, which is to say their centrifugal force exceeds self-gravity. So they're flinging out material from the star itself, right? So that very interesting stars. Altair is I think expected to be the fastest known rotating star. It's 250 or 280 kilometers per second at the surface. So that's at the brink of Keplerian breakup. Some others may have already undergone it, so we don't really know. But anyway, so these stars are hot stars, and because of their oblateness, their oscillations are very complex. So we don't really understand what's going on. The asymptotic theory of stellar oscillations, which describes all main sequence stars and red giants and so on, does not apply to this. So here's an instance of a delta Scuti spectrum. So some small class of these represent regular oscillations, periodic. You can see these. You can see this here. This is frequency in cycles per day. That's the metric used here. That's the units that are used here. Again, this is test data. So you take the time series Fourier transform, modulus squared. That's what we're plotting here. You can see they're approximately uniformly spaced, okay? This is what you expect of a conventional system on Earth, right? So you take a little metal ball and you tap it. You have the fundamental, first harmonic, second harmonic, so on and so forth. They're all uniformly spaced peaks. That's what we know and we think should happen. And so we find, so the first thing was, TESS has 63 sectors. And so it has hundreds of thousands of candidates. So we have to narrow it down, narrow it down, and then identify delta scutis from a variety of constraints. So we applied a machine learning algorithm, a different machine learning algorithm, first to build a data set of all delta scuti stars from the full test sample, which has an enormous number of objects. So, okay, so we found about 7,000 delta scutis. From the 7,000 delta scutis, we then wanted to detect, ignore this for now, how many of these are regular oscillators, because they seem to sort of indicate they follow the asymptotic theory, or a more basic theory of of oscillations. And so about 6% of these show regular pulsations. Once you have regular pulsations, you can get, almost nothing is known about delta scutis. I really want to say that people studied these objects for a long time. Nearly nothing is known about their interior structure, about their evolution, about their rotation, composition, age. Really nothing is known. Primarily because we don't have a theory of their oscillations. And so we can get their masses, of course, independently, but we get their compositions, their metallicities, their ages, even. So we have either young delta scutis, or they seem to do this bimodal age distribution. Okay, so we're able to get that. And then one remarkable result is we see a spin down of delta scutis. Now, typically, this Kubanich law, so let me just explain this. This is horizontal axis is age. This is cycles per day and rotation rate. Okay, so in comparison, the solar rotation rate is 0.04 cycles per day. Okay, so you can already see this is 0.4 is 10 times solar rotation, 0.6 is whatever, 15 times solar rotation, and so on. Okay, so this Kubanich, who is a decorated astrophysicist, found in the 70s or the 80s or something, that most main sequence, or a lot of stars, undergo spin down as they age. Okay, this is the Kubanich law. And the reason for the spin down is magnetic braking. So they all have magnetism, so they're all dissipating their angular momentum through magnetic braking. But when you reach a critical temperature beyond 6,000, 7,000 Kelvin, delta scutis are not cool stars. The sun is a cool star in comparison. We have a magnetic cycle, we have magnetic braking in the sun, we have wind, all of this stuff. Delta scutis don't really have strong magnetic fields. They have very weak magnetic fields because of this temperature, which destroys, or thought to destroy, dynamo type behavior. So we expect naturally that, in fact, I mean, when you think about it in retrospect, rather, that their rotation decay, the spin down of delta scutis ought to be much slower. And that is, in fact, from the small sample of 436, we found 38 of them, which have very distinct signatures of rotation. Again, it was all done with machine learning, and we find that there's a spin down that is a lot flatter than this Kubanich law here. Okay, so this paper is also currently reviewed, an unexpected and very nice result. The last thing I'll say before I finish is what I've been really excited about, actually, all of these results, is the development of a new theory driven by data. So this has been one of the promises of machine learning. You throw at it, you throw a sufficiently sophisticated machine learning model, a lot of data, and it will tell you what the underlying theory is, right? So that is one of the promises of machine learning. And there have been some instances, I don't know all the instances, I've certainly seen that some people derive Newton's law and so on and so forth, which is already known. But I want to detect new laws. I want to say what's going on. A law is a strong word, maybe a rule or a pattern, if you will, right? So as I said, these delta scuti stars are very, very complicated spectra, and I have this 7,000 stars. And what I want to know is, can I build a theory of what is driving the oscillations of delta scutis, merely from looking at their spectra? How can I do that, right? So these are very complicated spacings. They may not be linearly spaced harmonics. They may be more complicated things. So we decided to do the following. As I said earlier, we built synthetics. That's our bread and butter. There's no way to build synthetics for delta scutis because we don't understand their oscillations. So we're just trying it. We're just trying it out. We built something that very roughly looks like delta scutis, and we insert a theory. We speculate a theory. We say, well, let us speculate that this quadratic, the spacings are quadratic, or the spacings are based on transcendental relationship, and so on and so forth. And so you can speculate a theory, insert the theory into the synthetics, and then train a machine on the synthetics and say, detect which law operates in these stars, right? So the machine then classifies, saying, oh, I've detected a quadratic law, I've detected this law, I've detected that rule. And then we throw the data at it. And we say, okay, Mr. Machine learning model, can you tell me if there's one of these theories is operational in this delta Scooby star? And so, remarkably, we find that these stars, for instance, we've detected one class, and we want to try to expand this out, but that these are quadratically spaced. As I said, we understand simple systems like this table. This has a fundamental, it has a harmonic, first harmonic, second harmonic, all linearly spaced frequencies. But this is not linearly spaced, it's quadratically spaced. There is no way you could, you would have to train an MCMC with all the infinity classes of laws, right, of rules to try to detect this. There's no way you would do it by naked eye, of course, impossible to say. So what we find is that when we insert this, train a machine and try to detect it in the data, this was reproduced, and these are test data. We blocked out the TIC IDs, but there's a class of 100 stars which show very distinct high amplitude peaks that have quadratic spacing. So this is frequencies of each of these peaks, and the horizontal scale is an index. We don't know what these modes are. Spherical harmonics don't work for delta Scooties because they're not spheres. They're ellipses, ellipsoids. So we don't know what the labels mean. We don't know what that means. But we only know that these are quadratically spaced. Okay, that's one thing. So here's the argument for what is the meaning of this quadratic spacing, right? So if you have this fundamental harmonic, first harmonic, and so on, there are two things. There's a law first that holds, right? It says that they're linearly spaced, or they're quadratically spaced, or transcendentally spaced, or something. That is a law. That is just it's a set of symbols. But there's also a time scale, right? So for instance, in this linear set of harmonics, if you remove the frequency, the fundamental frequency, then you get integers, 0, 1, 2, 3. Those are integers, right? That's the first harmonic, second harmonic, third harmonic, and so on. So there are two things here. One is a law, and one is a frequency scale, or a time scale. Okay, so in this case, we're looking at a distant star. We look at the global properties of the star because we cannot resolve the disk of the star. So there are only two parameters that govern the frequency scale here. Either the rotation rate, which is a global feature of the star, or the acoustic travel time of the star. So the breathing mode of the star, right? So the acoustic travel time from the surface to the center and back. Just the sphere pulsing. There's a zeroth order, this is probably the zeroth order mode of this table, right? So that's the breathing. There are only two time scales or frequency scales involved. We know that for delta Scooty stars, the frequency scale associated with this breathing mode is about 5 to 8 cycles per day. And then we find, therefore, that all of this quadratic spacings can only be explained if it is rotation. So it's about, we find that the time scale or the frequency scale that you need to remove is about 1 cycle per day. So you can see the cycles per day here. This is the parameter. So if you remove this number and you apply this law, then all of these collapse into integers, 1, 2, 3, 4, 5. You can't have integers in physics unless you've removed all the time scales, you've removed everything, right? The law, everything. All of that has been removed. So these two things, the law and the time scale, basically convert this system with units and all of this complicated things into integers. And so therefore we find that these basically can only be explained by the rotation rates of these delta. I mean, this number is the rotation rate of the delta Scooty. As I said, there are very few stars. The delta Scooties can only be inferred through V sin I measurements, spectroscopy. That can also change quite a bit. If you look at V sin I measurements in November, and you look at it next year in December, they'll probably be very different measurements. They're not even consistent measurements. So from these pulsation frequencies, we're able to estimate the rotation rates. And again, we find something very interesting. For these 80 or 100 stars, we've discovered a new law, and we've discovered the time scale associated with that new law, which we think is the rotation rate. We don't know, right? We don't know that it's the rotation rate. This is a hypothesis, and I provided arguments to support this hypothesis. We find that the rotation rate, in fact, decreases with the rotation rate increases with decreasing temperature, potentially, again, implicating this theory of the magnetic field, right? So in cooler stars, cooler delta Scooties, magnetism is more likely to operate As they grow hotter, magnetism is less and less likely to operate. So these are more spun down than these are likely to be, regardless. So we expect to see a general pattern like this. So with that, I would like to end, and thank you very much. That's it.
Yeah, you mentioned in passing that you suspect the machine learning gives you better results than the MCMC.
So it's interesting, actually. People say, oh, machine learning is a black box, so if I take a minute to explain again, everyone says, oh, it's a black box, but when you really get down into the weeds, MCMC is also actually a black box. And when we look at it, it's far less flexible than a machine, because we put in all of this, the MLE and the maximum library, all of this stuff, and then it ends, there's an argument that I've forgotten, but it tends to constrain the problem in some unusual ways and does not allow it the freedom that, I'm sorry I'm using all of these hand-waving terms, but basically it's, we find that this thing is doing better than it. Like we look at the fits finally, we look at a fit, an MCMC fit, and then we look at this fit that we get from this, and we find that this actually does a better job at fitting than the MCMC. And it's of course a billion times, if not, I didn't put the number down, but it's a billion times faster than MCMC. So it is better than MCMC both qualitatively and quantitatively. That's the way I think about it.
Yeah, so it showed very nice talk. So a lot of these problems are basically, you have some model which has a few parameters and you can predict something that has thousands of data points, and then you're trying to invert this very complicated structure. There are two questions here. One is that, do we know that this is a 1:1 connection, or if there is any degeneracies which would feed back in? So are there degeneracies, and do they come out of your the machine learning framework? And secondly, what happens if the model is not really completely correct, and there's an asymptotic model, we don't know whether it is absolutely correct, and then would it try to fit something, just make it as close to as possible, and then can we identify these catastrophic failures?
That's a good point. Yes, we have not detected any. But I mean, the delta scooties, we have no theory of oscillation, so that's an instance where it's a complete failure of the asymptotic theory. But for main sequence stars and red giants, we have it pretty well nailed down. There may be instances, we have not detected those instances, but there may be unusual oscillations. Usually those tend to be binaries between a red giant and a delta scooty, and then you average the two spectrum, the light curves of the two are basically being summed together. And so you see some set of modes that you can explain and some anomalous set of modes that you can't. We have not yet detected a case where we know conclusively that it is a main sequence star which is producing unusual oscillations. That would be very exciting, actually, also.
I had a related question. So this relation that you showed between Q and delta, additional methods for seeing of flattening.
Yeah.
So how much of it is because you use the models themselves to make the simulations, and whether these laws, I suppose, or this kind of correlation would be pre-existing in the model itself?
Oh no, we have a complete.
So that is not there. It's just
no, yeah. So when I say simulation, I should specify. We're not using MESA. We're not using anything. So we have these parameters, right? So these parameters over here. When you specify Q, when you specify W, the theory of oscillations tells you something. There is no intrinsic physics. There's no the stellar physics is not here.
So MESA is not used to predict.
No, it's not. It's not. So Q is decoupled from the other things. There are two things. The Q influences the amplitudes of these, and in these conventional methods, they're not taking necessarily that into account. The machine is seeing all. It's seeing everything.
Okay, so let's thank Sharon again. I just had one quick thing that I wanted to show. So this is about tomorrow. So we are going to have this hackathon tomorrow. And we ourselves are brainstorming how to do this optimally. But we will come up with a plan until tomorrow. But for the moment, we had put up a board here outside. And during the tea breaks and so on, many of you have put in some project ideas. So there are 10 already on the board. So many thanks for that. What we are proposing to do is the following. So those who have written a project or proposed a project outside of the board, for tomorrow, kindly prepare a one-slide summary of the project so that you can give a presentation about what it needs to be done, what kind of data sets you are looking at, and what is the goal that you would like to achieve. We are not expecting you to know exactly what kind of machine learning methods need to be used. So this is something that you guys can brainstorm together and figure out. Okay, so that's the idea. I would propose that you add your slide to the following Google slide deck so that it will make it easy. In fact, it is the same exact slide deck that I'm showing you right now here. So that it is easier for you to remember, I've created this tiny URL. So DSW, Data Science Workshop 2023, and capital H, hack. Okay, that's it. So if you remember this, then those of you who have proposed these ideas, just go ahead and add a slide. If more of you have ideas, you are more than welcome to also add these slides to this particular slide. Then for all of us, we need to create an account on sciserver.org. So this email had been sent to you before. So just remember this particular website. And on this website, please go there and try to familiarize yourself with the interface. So you can actually launch things like Jupyter Notebooks. You can install libraries already. There are some pre-installed libraries which come with the Jupyter Lab on sciserver. So things like TensorFlow, for example, are already installed so that you can use many of the libraries that we have been discussing yesterday and some of them that were mentioned today. They may already exist or you may have to install them using Python. So just take a look at what needs to be done and what can be done. So just familiarize yourself with this interface. And then finally, project proposals, they should upload their data in the Scratch folder. So if your data set is too big, your home directory will not be able to accommodate that particular data. So put it in the Scratch folder. So I myself have uploaded something like 2.2 GBs of fixed files right now, and that's not a problem. Sciserver is able to. So please try to do that. And keep an example Python script ready, which can tell you how to visualize the data, or at least some part of the data. So if you have, I have like fixed files. So I have a Python script which I have kept ready, a Python notebook, which will tell you how to read that fixed file and how to create a PNG image out of it. So that it becomes easier for people who want to play with the data, just to visualize it and what needs to be done. Okay, so that's the basic thing that I could come up with so far. If you have more ideas, please let us know, and please, you may have gotten a mailing list invitation as well, many of you, at least all of you.
All of you.
All of you.
Whatever the email list you sent me yesterday were added.
Yeah, yeah. Okay, so whoever were in the invitation list have been added to the email list. If you have not gotten the invitation, please contact Yogesh and he will add that. Okay. Okay. So this is there are some. Yeah, there's one more thing. I had been asked whether the recordings of the talks will be available or not. So the recordings will be available. So we are making these recordings as we go along, and so you can find them on YouTube. The YouTube link is crazy, so that's why I again made a shorter link. So that it's easy to remember. Again, DSW 2023, December 12th is yesterday, December 13th is today. Okay. And then next we will have a photo in the Kund area, like right now, after which we'll break for it. Okay. Thank you so much. Yes, there is one more thing, sorry. There is a public talk which will be given by Ashish today, and that is at 6 p.m. Right, 6 p.m. That will be in the Chandrasekhar auditorium. So all of you are welcome to attend the talk. There will be like members of the general public.
Okay to leave stuff here, or should we take it?
No, you should take it. Thank you for